Okay. Hello, everybody, and welcome to our third and final exam prop of the semester. Um, this uh, exam is going to cover NP complete and linear programming. I'm not going to go over any of the linear programming today. I will go over like just enough to like let you know that it's on the exam, but not really go too deeply into it. To me, it's linear programming is just remembering math, right? So like you remember the formulas, you remember the conversions, you remember what each part of the thing means. There's no like trick. I don't think there's any real trickiness to it other than just memorizing the mathematics of it. So I don't think it's going to be very useful for me to go over it. And then there's a great post by Emily about like all the details of linear programming. So if you are struggling, I suggest going over that more. Um, so again, your voice and video image may become part of the recording. So if you do speak or you do put on your camera, note that it'll be might be seen by those who are watching the recording later. Um, so I actually haven't confirmed this with Dr. Brittle, but I think this is going to be the exam layout. It's been the exam layout for this exam before, so I'm pretty sure it is, but there will be a final post on like what the exam layout is, so pay attention to that. So it's going to be 2 NP complete reductions and then a set of multiple choice questions. You've seen this exam format basically before, and it'll be very similar. And again, there's 20 points for each section for a total of 60 points. All right.
Hey,
So
sorry, I've got a
yep.
quick question about that exam format. I guess, have you seen or do you expect there to be any like generalization reductions? Just because I know we haven't seen a ton of those thus far in the course.
So I will go over that slightly, but so the way generalization reductions work in is that you take a known problem, right, that you know is NP complete, and you see this unknown problem, and you go, you know what? If I just make a few simple tweaks of this unknown problem, I actually make the two problems equivalent. And by claiming that the two problems are equivalent, you can sort of shortcut the whole like, you know, uh, if and only if correctness by saying, well, these two problems are equivalent through the transformations I've done. And so if one is NP complete, so is the other one. You do not want to do that on the exam. On the exam, you are not going to get an opportunity to approach a problem using generalization. So even if you know what generalization is, even if we just kind of go over it quickly, all the problems on the exam are going to go for the full reduction. You're going to have to do the input transformation, the output transformation, and then you have to argue the if and only if in both directions. There is no shortcutting that. Um, I think we present some of the generalization problems for you to kind of familiarize yourself and recognize that these two problems are basically the same with a few changes, and we change it back to make them equivalent. All right. So NP theory, um, we are concerned about what's polynomial runtimes, and polynomial runtimes I consider O to the n to any k that's a constant. So if k is a 1, 2, 3, 4, 5, we consider that to be a polynomial runtime. And then we have what's considered exponential runtimes, where it's O of k to the n for some k that's greater than 1, and then n is something that can change. So we think in previous topics, we were very concerned with like how fast your runtime can be, and it's like O of n versus O of n squared versus O of n log n. They were all considered very different runtimes, and you want it to be as fast as possible. In NP theory, we are concerned with the classes of runtimes, or like the hardness of what we think is a good solution for a problem. And in that case, the line is drawn at the polynomial runtimes and exponential runtimes. So we're no longer considering like is O of n and O of n squared versus O of n log n, which is faster. In this topic specifically, we just care if it's polynomial or if it's not polynomial. And then there's this like in between thing called pseudo polynomial runtimes. I don't know how well the class has been discussing this. There tends to be a lot of confusion around the idea of pseudo polynomial runtime. So I'll go over that in this office hours. But know that this is when we talk about pseudo polynomial runtimes, we consider this to be basically exponential. We call it pseudo polynomial because they look different and it's kind of weird. So we want to address them and call them out. And so pseudo polynomial runtimes are considered, and this is the way we say it, polynomial to the magnitude of the input, but exponential to the size of the input. And so it's important to understand what the magnitude of the input versus the size of the input is. When we talk about size of the input, it normally means that like if you add one more to the size, you are basically adding some constant number of bits to that size. So if I was to represent an object, it may take like 4 bits. If I have 2 of them, I have 8 bits. If I have 3 of them, I have 12 bits. Right? That's my size of that input is increasing. And this there's some estimation there, but that's basically what it means. Whereas the magnitude of the input is like when you're doing knapsack, when you consider your your budget or your sum or whatever, like those numbers are ooh, strong echo there. Okay. It's a number, but the representation of that number does not increase like in more bits. And I'll show you an example of that in a second. So P here equals polynomial, runs in polynomial time. NP means non-deterministic polynomial time. It means that it can be verified in polynomial time, but may not be able to be solved in polynomial time. And so the question is, does P equals NP? And then we don't know. The question really boils down to if we can verify a problem in polynomial time, can we also solve it in polynomial time? And this is the question that computer scientists haven't been able to prove. We have an intuition of which one it is, but it turns out that proving it one way or the other is incredibly difficult. So that's where we are. Okay. And then is this true for all problems? So we know that for some problems that, and these are considered the P problems, where if it takes polynomial time to verify it, it also takes polynomial time to solve it. And then there's some problems we don't know if that's possible. All right, so the pseudo polynomial runtimes. Consider this, knapsack. We know in for Fulkerson, which is OMC, is also considered polynomial. Where n and m are based on the size of the input. So like say n objects, m edges, or n vertices, m edges, right? Like as you add more edges, you get your m increases, and it actually represents like an additional object that you have to represent. Whereas B and C, this budget and this capacity, they're considered magnitudes. They're a single number that increases the runtime. So each time I increase one of B, or one of C, I'm actually increasing the runtime, but we don't need more space to hold this number, right? So if you think about it, suppose M, and it doesn't really matter what M is, right? It's arbitrarily represented as a 32-bit number, so if I have one edge, I need 32 bits to represent it, 2 edges, 64, so forth and so forth, right? Like if I double the number of edges, I will have double the amount of space I need to hold it. And so when my runtime increases, it's increasing as a polynomial through the actual increase in size. However, because C is a number, if I wanted to represent a 1, I use 1 bit. 2, I want to represent 3, I still use 2 bits. And then 4, I increase, but again, 5 is representing 3 bits, 6 is representing 3 bits. So because this increase is not a linear or polynomial increase, we consider C of the input not to be polynomial, and so forth and so forth. So I go on for a bit because I can't get it a bit now. I wanted to show that at 4 bits you start representing a lot more numbers than 1, 2, and 3. Okay. And then someone has their mic on, if you don't mind turning it off. So we can say that C is represented for where C equals some number is approximately to log of n bits, right? And that is our representation of C as a number. And so we call this a pseudo polynomial runtime, where it is polynomial to the magnitude of input. So at say 16, I might need 16 runtimes or whatever. So it's polynomial to the 16, but the exponential of the size to input. So if I have 16, let's say like the runtime is 16 something, right? And the space is only 5 bits. From 5 to 16, you consider that to be exponential because it's you multiply it several times. And so the reverse is also true. So like any runtime that is based on log x is considered polynomial. So if you were to take a log of C, you have taken that exponentially increasing runtime based on the space, and you brought it back down to polynomial. So log C is considered to be polynomial, but a runtime based on just C is not considered polynomial. It's not considered polynomial, and therefore it is pseudo polynomial. Okay. Does anybody have questions about what pseudo polynomial means?
I have a question. So it's not possible to prove that algorithms with pseudo-polynomial runtimes are in the class NP because you can't do a reduction for them NP hardness or for checking in the class NP. You can't do that in polynomial line.
Sorry, you're asking, can I prove that a problem is?
Sorry, I'm just because in the lectures there was a section considered for a knapsack, and since it has a pseudo-polynomial runtime, it's not possible to reduce it from another class. Maybe I misunderstood it, but just want to know if we can reduce other problems NP to problems which have.
So a problem that has a pseudo polynomial runtime is considered to be in the class NP hard. We consider that to be exponential. Like I said, pseudo polynomial just means that it has an exponential runtime, but it's confusing because you don't see it being like, when you say in capital B, you're not seeing any exponents, and people go, well, that's not exponential because there's no exponent to this runtime. But it's only because of how the magnitude is represented that it's considered pseudo polynomial. But if a problem is pseudo polynomial, it is in fact exponential, and it is in fact considered to be NP hard. You can reduce from into knapsack from other NP hard problems.
Okay, I understand. Thanks.
Yeah. In fact, from or to knapsack, and subset sum is considered to be NP hard or NP complete. Okay. Okay, so we got that. And then there's a section at the very end of the lecture. It's called undecidable problem. And so there is a confusion between the hardness of a problem and the solvability of a problem. Okay, so we don't know if all hard problems, such as NP hard problems, can be more easily solved. That we don't know. We do know through a paradox by Alan Turing that there are some problems that are just not possible to solve, and these are called undecidable problems. It means that you are not able to get a consistent output through various things. One of which is the paradox of the halting algorithm. So there exist problems that just some input just cannot be solved. Okay, that's a fact, right? And the problem is then considered computationally impossible with unlimited time and space. And in fact, you can actually prove some of them to be impossible, even with very short time and space, just through the exercise of the halting problem. And it's not even whether a problem is undecidable or not, actually doesn't have anything strictly to do with the hardness of it. Okay. So let's recall what a decision problem is. Is that a problem that can be posed as a yes/no question of the input values? An undecidable problem is a decision problem where a yes/no cannot be determined for all inputs, all valid inputs. It's not trying to trick you. It's not saying, okay, well, if I ask for like a graph algorithm and I threw it some random non-graph, it doesn't give me a correct output. It's saying if you had a valid input based on the program, I still may not have an answer for you, and that's how an undecidable problem comes to be. And then this is different from having no solution. There are some, like I said, like if you have an invalid input, you may not have a solution. Whereas a undecidable problem is it's impossible to have a yes or no on that valid input. And remember, some NP complete problems, right, does have no solution. It means like, if I can I find a click of size k in this graph, and if yes, give me a solution. If no, say no solution. And so no solution is a valid solution, right? Whereas a undecidable problem actually just doesn't know what the valid solution could be. And so this was proved by the existence of undecidable problems back in 1936 by finding an example and the now famous halting problem. And I know the halting problem can be a little difficult to wrap your mind around, but just know that you basically can't come up with an answer. So given a program P and the input I, decide if P of I will terminate, which is to stop running. True if it will terminate, false if it will not terminate. And there's an infinite loop. We can create a paradox such that we can't determine the answer. I think the book presents one version of it in sort of pseudocode. I did one in sort of Python, but I can't actually code this out. So I put in a comment here. And so there's a function that tells you if a function will hold. So it returns true if the function holds, and it returns false if it does not hold. And calling this messed up so that, while will hold of this function, okay, so we keep calling this, and while this is true, we keep looping. If it's not true, we end the program. So now the question is, will this actually terminate, right? And it's sort of unknown because it's a paradox to itself. If you say yes, then I will make this program keep looping, resulting in a no. If you say no, then I will exit and I will result in this program being yes. So because of this paradox, we actually don't know what this program could possibly do if we were able to write this program. And so this is how a halting program is presented. Okay. Any questions on the halting problem and the undecidableness of a problem? Okay, cool. And so the meat of this topic in this exam is going to be NP complete reductions. And so this is the basic structure. You have some algorithm, call it F. Oh, sorry, no. Okay, some algorithm A and some reduction to algorithm B. You want to take a input to A. You want to create this transformation function such that we can pass it into the algorithm for B. And then on output, you want to have this output transformation function such that we can output it as a solution for A. Okay, and then you want to map it so that if algorithm B has no solution, then you also have no solution for algorithm A. This is the general setup. This is the setup for like all reductions in general, but it's especially important. Well, not especially. It's what we use to prove NP hardness of problems. So A is considered to be the known problem in this case, and B is considered to be the unknown problem. You want to solve the known problem using the unknown problem. You don't care how the unknown problem works. This is a mistake a lot of students will do. Is like, okay, well, my algorithm for B does this, and this is how it works. You don't know how it works. You're just given a problem a algorithm, a problem B, and we want to prove that this is a hard problem. We don't know what solution to this problem is. We just want to know if it's a hard problem, and that's it. So don't try to write an algorithm for B. So you write in the input transformation, which is function f, and then the output transformation, which is function h. Okay. And so this is the direction you always have to do your reduction from. So it's A to B, or known to new, or known to unknown. You can use any of these to try to like remember it, proved to unproved, the problem you pick to the problem we give to you, the proven NP complete to what you are proving to be NP complete. Right off the bat, we have started telling, like, students weren't really paying too much attention to this issue until we really just told every student, if you do the reduction in the wrong problem, in the wrong direction, your entire reduction is going to just be marked wrong. There is no way to recover from a wrong direction reduction. So it's just going to be minus 16 points. You lose all the points in your reduction. You can still get 4 points in the NP proof, which is a separate section, but the entire reduction is just marked wrong. So do not make this mistake. It is not something you can really recover from. Okay. And there's no point in arguing with us on this. It's a very standard rubric. If you argue it in the wrong direction, it's just going to be minus 16 points. There's no way to argue like, oh, I got some of this correct. I got some of this. This sort of makes sense if you take it in this way. It's a very standard reduction, and not much you can do about it. Someone have their hands up?
Yes, I have a question. For example, if you are trying to solve some kind of graph problem and the input is not given in graph format, for example, describe the problem statement. So if you go back to the previous slide, so I know I have to do the input transformation for the unknown problem. That is true. Do I also need to include the transformation for instance I, for algorithm A, that I need, let's say, can I just call, I have a graph G, or do I need to reduce the given problem into the graph like we did in part 2 of this course, right? Like we have to create a graph and then give that graph to algorithm A, and then now transform using F into the input to algorithm B.
You absolutely have to. Your transform, that becomes part of your transformation. If you are given a non-graph problem and you are trying to prove okay, so you are given a graph problem and you want to use a known problem that's non-graph and you want to turn that into your algorithm B, you have to make it the input valid for algorithm B, right? So this happens in a lot of NP reductions, like say from SAT to a graph one, or a graph to a SAT one, and it goes both ways. Like if you are coming in from a non-graph problem into a graph problem, you have to transform it. If you are coming from a graph problem going into a non-graph problem, you also have to transform it. You have to say what each vertice is representing, each edge is representing. It is not given to you. Like that is actually the core of what you're doing. So to ignore that completely, you're just basically doing no transformation.
So that makes sense. Also for algorithm A, let's say if I'm modifying the given graph, let's say I'm adding some vertices or something. So do I need to mention that in input transformation that I'm going to modify my graph? That modified graph will be feed into algorithm A, and then I have F. Of course, I have to include for F. But
you are going from a known. Okay, so this part is very important. So be very, very careful. Okay. We tell you what problem B is. We tell you, hey, I have this unknown problem. Try to prove to me that it is a very hard problem. Okay. You pick your algorithm A to wrap around algorithm B. You can pick whatever NP problem that we have covered in class. You do not modify the input to algorithm A, because the input to algorithm A is all valid inputs to algorithm A. There is no such thing as like, okay, well, what if a graph has this? Let me manipulate it to a better input for algorithm A. The inputs to algorithm A is all valid inputs. What you have to do is take any valid input to algorithm A and transform the entire set of possible inputs to algorithm A to a input to algorithm B. And the other thing you have to be very careful about is that you don't have to consider all possible inputs to algorithm B. Algorithm B might take more complicated inputs, but if you're wrapping it around it with an algorithm with A, you only need to care about the inputs to A and making that a valid input to B.
Makes sense. Thanks.
Okay, cool.
I have a question. Is it
Okay.
possible that when we try to prove NP completeness, is it possible that A will reduce to an instance of B?
So I will say that it is technically valid, technically possible. The questions in this class are not designed to do that. You are not going to be given a problem where what we consider the best solution to be do this to A, run B n times or some polynomial times. It is a valid transformation because it is still a polynomial runtime, but that is not going to be your most direct solution. So I would say that if it comes to that, if you're seeing that, okay, I'm going to have to run algorithm B n times, you're probably missing like a more direct transformation. But at the same time, if it comes to the point where this is the only solution that you can come up with, and you can't come up with a more direct transformation, we will grade it. And if it's a valid transformation with multiple runs of B, it'll be okay.
Okay, thank you.
Yep.
I just want to say, it looks like John Paul has a question in the comments. He said, "Hey, Joves, how do you approach NP-complete reductions and decide on what kind of reductions to make?"
I always find these kind of questions like to be really funny to me. It's like this entire office hours is going to be around my approach to NP reductions, right? Like that's the whole point of this office hours. So I think you're just kind of putting the cart before the horse. Like I will get to that, obviously, hopefully. All right. All right. So NP complete proofs. We give you a problem B. You want to prove that it is NP complete, and then you pick a problem A to reduce to B. Okay. You want demonstrate that problem B is in the class NP. So there's two different classes. There's NP complete and there's NP hard. NP hard means any problem that we don't have a known okay, in the scope of this class, right? Because there's actually there's more difficulty classes beyond NP hard. But for the sake of this class, NP hard is any problem that we don't know a polynomial solution for. Okay. NP complete is problems that are NP hard, but we have a polynomial verifier for. Okay. And so when we want to prove that something is NP complete, it's actually two separate steps. One is to prove that it has a polynomial verifier, and one that it can be reduced from a NP hard problem too. Okay. So that's why this first step is to demonstrate that the problem B is in the class NP, and NP means that it has a polynomial verifier. Okay. So give steps on how to verify a candidate solution B in polynomial time. You must prove all requirements. Okay. You don't know if we gave you a working solution. You know we gave you a valid format of that solution, but you don't know if it's a working solution. And what that means is that you're not going to have to verify that the solution that you're trying to look at is a graph. You know it's a graph. You don't have to verify that it's a SAT assignment. You know it's a SAT assignment. What you have to verify is all the different requirements. Is the solution a clique? Is the solution an independent set? What is the size of my solution? I have a target that I have to verify. Is there a goal? You have to verify all these parts. So basically, take what the problem statement is And what I normally do is, as I read the problem, I start typing up, writing down what I think the requirements are, and then when I do my NP proof, I go through and I verify each of those. Okay. Yep, I will do that, John Paul. I will go over how I approach each problem. Okay. All right. So you don't need to prove junk solutions. We're not trying to trick you. We just don't know if this is a solution, right? Think about it as like, you sitting next to me and we saw this algorithm, see this problem. I go, oh, I draw this graph. Hey, can you take a look at this? Is this what the problem is asking? Can you verify this is a solution? And so you would go through, you would look at the graph, and you go, okay, I see this. I see a click. Yes, I see that it has k indices and stuff like that. But I'm not going to give you one that's like, here's some random non-graph solution. Okay. The runtime, you have to give a big O runtime. This is polynomial is not enough. We need the specifics of how fast your verification step is. You need to tell, just like you do runtime analysis, you got to give us to the right runtime. Okay. This is constant is generally considered okay. You shouldn't do it just because it puts you in like a bad practice. But this is a constant runtime is equivalent to O of 1. We take that as what that is defined at. A polynomial runtime has many runtimes that could be considered polynomial, whereas a constant runtime is defined as O of 1. I would still avoid this. I would still just give a big O runtime just so it's easy for your grader to find. If this is hidden somewhere, you might have to do a regrade. And then this is key, and I'm going to explain why. You don't want to give it in terms of O of K, O of B, O of G, unless you bind it. Okay. And what that means is that when you are given a, like say a click problem, and you say, with a budget of K, remember how we said that the number K, B, or G is considered magnitude. And so if you give a runtime that's in terms of the magnitude, it's considered pseudo polynomial. It's no longer considered to be a polynomial verifier, right? Like if you had like 100 vertices in your input, and I set k equals to like 1,000,000, right? You're no longer having like a fast runtime. Like that k could be some like unboundedness. However, what you can say is that knowing that k is less than or equal to n, or g is less than or equal to n, this runtime is O of g. So by binding it, you've set an upper limit to these magnitudes, and therefore it becomes polynomial because you've bound the number to the input size. I would still avoid it. I would just say O of n or O of m. Like there's no reason to go this extra step, but just for your benefit, this is how you would do it. Okay. Okay, you guys are having discussion.
How much detail should we present about the runtime for each step? Like sometimes I claim I can do this in n times m or n times m squared. Do I need to put an explanation on how I come up with this? What kind of implementation I do to arrive at this?
I would give a runtime for every requirement that you are verifying. 2, I would any runtime that we have given to you directly in class, you're allowed to assume. So all of n squared to verify a click, all of n squared to verify an independent set. You can do that. However, if you give a runtime, be very careful. You have to actually explain why it takes that long. So for example, if I said it takes O of n squared to verify a click, that's simple. Everybody kind of understands, okay, you're checking the edges between everything, it's O of n squared. Now, I could, if I wanted to, say it's O of n to the fifth, right? Like if I said O to the n to the fifth, it's still a polynomial runtime, but it doesn't match what the understood way to do to uh, to do to verify click. Now you can be, if you feel like you want to be a joker, I've always joked that I'm having more confidence in my own NP complete proofs. I might, as a joke, have done, well, I verified this to be that there's a click in O of n squared, and just to be really, really sure, I do this n times for n runtime of O of n cubed. Like that technically is okay, but if you put down O of n cubed, there better be a good reason why. You better explain why it's O of n cubed, rather than the understood O of n squared. Does that help at all?
Yeah, thank you.
Great. All right. So again, it can be as slow as you want it to be, as long as it's polynomial and as long as your runtime is correct. I think a lot of students, and I'll go over like the most common penalties of homework 7 to 8. I think a lot of students don't realize that their runtimes have to still be accurate just because their runtime can be really slow. And I always say this to students: when you're doing a NP verification, it's better to be slow and correct than to be fast and incorrect. If you're unsure of how to get it all like n way to verify something, but you know a very brute force O of n squared way to verify something, just go with the O of n squared way to verify something. It doesn't really matter for this topic. You can put an O of n squared runtime as long as your verifier is very, very correct. So don't try to be what's word? Don't try to be like overly efficient or try to be overly smart about this. Just go with the solution that you know is correct and then get the correct runtime for it. That's it. All right. And again, correct is much more important than fast. So as long as it is polynomial. And then the second part is to demonstrate that B is at least as hard as your chosen A. And so you do this by showing how an instance of A that you've picked can be converted to an instance of B in polynomial time. All instances your unknown problem could take in more inputs, but as long as all your instances of A is covered, then you're good. You do not get to choose the input of A. A has to be valid for all inputs of A. And you want to force a solution to B if there is a solution to A. So if A has a solution, B must have a solution. Okay. And then this also must be a runtime in O. Do not give it in terms of K, B, or G unless you bind it, same as before. And again, it can be as slow as you want it to be, as long as polynomial. And never, ever, ever try to solve A to create an instance of B. Okay. That is a problem.
Sorry.
What was your homework 7? What was your homework 7?
It was called Spider-Verse.
Okay. So the thing with Spider, that like let me just finish this thought and I'll answer question.
Yeah, you get it.
The thing with Spider-Verse that some students will do, and as a huge penalty, is you'll say, okay, well, given the click problem, I want to turn that click problem into a Spider-Verse problem. So find the click in the click problem and add links to it to make it a spider in the Spider-Verse problem. That's a big no-no, because in order to find a click in the click problem, you've already blown your polynomial runtime, right? Like if you could solve problem A so easily, there wouldn't be a reason to try to reduce it to problem B. So do not try to solve problem A. Do not try to find the click in the click problem to do what you want to do with it. You have to make it very general, such that if there's a click in a click problem, it'll have a spider in the Spider-Verse problem. All right. What's your question?
Hi. So for whenever that line that says you do not get to choose the input of A, I guess that makes sense on the level of if you're choosing, clique, it needs to be a graph problem, or if you're choosing SAT, it needs to be like a CNF. But if we're given a situation like with homework 8, which was the city planner Computopia problem, where it's like we know there's n neighborhoods, and when there's m potential locations to service those neighborhoods.
Yeah.
Is it okay for us to say something like I used set cover for the problem, so I said the input to set cover is up to M sets, each containing up to N items. Is that like acceptable to, because it's like, I don't feel like that, I feel like that is choosing the input in some way just to match the problem, but it's not like morphing the input in some way. But I know that it was valid to do vertex cover or any other number of the NP complete problems for
Right.
the problem.
So I think that's a slightly, like, I understand what you're saying, but that's a slightly incorrect way to phrase it. What you can do is you can choose set cover. That's fine. But your set cover, the set cover problem has a known input like signature. Basically, it does take in M sets. It does take in unique items, and that's that. What you do now is that now that you have that set cover problem and you go do whatever you're transforming to it, you say, my N unique problems, unique items map to this. My M sets map to this. You can't take your problem B and arbitrarily set a restriction around your problem A. You take what A gives you and you redefine anything to what to the restrictions that B have. So like
Okay.
if B has a restriction K and A has no restriction, right? You can't say A must be limited to K because it doesn't work like that. You're reducing from A to B, not the other way around. You don't know anything about B when you start with A. What you can do is once you get to B, you say set the K to N.
Okay,
You can
and
work
that
around
makes
the restriction
that
for
much
B,
makes sense
but
to me. But I
okay.
guess like part of the reason why I chose set cover instead of doing something like a vertex cover for homework 8 was because I didn't know how to phrase that there is a graph going into that problem, because nowhere in homework 8 did it say that Computopia is laid out in the way that it was laid out in previous like graph problems about Computopia, if that makes sense.
Right, but you're doing the transformation, right? Like the what that graph becomes for the neighborhoods, and I think what sports facility.
Yeah, sports
I've
facilities.
actually never solved this problem. I just kind of glanced at it. Is that you define what your input to A is in terms of your input to B. That definition of how those input goes from one to the other is the thing you're doing. That's the transformation algorithm that you are tasked to write. So it's not going to be something simple like everything from A maps perfectly to everything from B, because then it would just be the same problem.
Sure, and that makes sense. But like, I guess like it was an extra layer of confusion for me, because like if I pull up homework 8 and at least like the wording that was used, it says city planner of Computopia is tasked with planning a number of sports facilities. There's N neighborhoods in Computopia, and the city planners are
Right.
given a list of M strategic facility locations.
Right.
The city can build MOSK facilities, and then it gives the example of what the input list to the allocation problem would be. So that signals to me that I need to take whatever the problem that I choose to use in my reduction, and whatever that input to that problem is, I need to map that in a way that it matches what the expectation for allocation is. That much makes
Right.
sense to me.
Right.
But how do I know how that like, I know that there's a set format for what the input needs to be for the problem that I'm choosing to use in my reduction. How do I know how to set that up in a way that it's not like, do you understand what I'm asking?
All right. So think about this from a programming perspective. Might be easier. So you are writing some function that has a function signature, right? It has input. It might have an extra number to it, right? And you
Sure.
want to call a method from a library, okay? That method from a different library may not have the exact same inputs as the one that's in your method, right? So the function you're writing. So you have to take the input to your function, do some work to it so that it becomes a valid input for the library that you're calling. You cannot read the library and impose the library's restriction onto the input that you're taking in, right? Like it doesn't really make much sense that way. You take whatever that input of your function is, and you do the transformation to get it correctly done for the library. And that's what basically you're doing. Like you can't impose a restriction of problem B onto problem A. Problem A has had its signature or its input already well defined. What you have to do is take those inputs and rearrange them or transform them into such a way that problem B can solve the problem for you.
Yeah, and I think there might be a communication gap here in the way that I explained the problem that I was having, like getting over the mental gap, is that I matched what the expectations would be for set cover going in as my problem. Like I know I wrote it in a way, or at least I think I wrote it in a way that matched what was in the textbook for set cover search as like the expected input in terms of what was given as problem information. But when I read your line, you do not get to choose the input of A, that sort of gave me pause.
You do not get to you do not get to say a specific input of A. Input of A is already defined. You can't say something like, I want to take in a set cover problem that only has 20 sets. You do not get to say, I want a set cover problem that only has 5 unique elements. Like you cannot impose a restriction onto your set cover
yeah,
problem.
and whenever I define my sets that were going in, I used it in terms of N and M from the allocation problem. So that was okay. So you're trying to say that we can't impose restrictions on the inputs of the problem.
Like basically. You know how okay, so you know how like the SAT problem is NP complete for for general SATs. If I was to say for my transformation, I want to take a SAT that only has clauses with 2 items with 2 literals in them, I have immediately caused that SAT problem to be a P problem. And if I was able and allowed to do that reduction, I have just proven that P equals NP. And so that is why it doesn't work. I have to take the generalized version of SAT and not be able to impose restrictions on it for my reduction.
Okay.
Okay. All right. What was that? Okay. And then the second part to this NP complete proof is to show how a solution to B, provided your transformation here, can be then converted to a solution of A in polynomial type. All solutions of B must be converted to a solution of A. So you can't skip solutions. If B has no solution, then A has no solution. Like I know that this seems like a nitpick line, but you should always have to write this in some way. Okay, because there are some transformations where you do something special with the non-solution step. In this class, generally, if B has no solution, A has no solution. But you have to be able to say that otherwise there's no way to return a no solution to A. So this is actually like I think one or 2 points. So you got to make sure you say that. Again, the runtime must be in big O. Try not to do any K, B, or G unless you bind it. It can be as low as you want. And okay, so that is the transformation steps for the NP complete proof.
For the second step, when you are trying to transform the output of B into A, and you want to show it is polynomial in input size, but the input size of B may be different from the input size of A, right? So, so you are going to formalize your reasoning that it is polynomial in the input size of B, and since the input size of B is polynomial in the input size of A, hence eventually the runtime is still polynomial in input size of A. Is that the correct reasoning?
The runtime of both the input transformation and the output transformation is always based on the input to A. It is always based on wait, hold on. Let me don't write that down. Let me think. Okay, and it should be based on the runtime to A. Yeah, it should always be.
It should be A.
Yeah, it's it's based on the runtime A. Yeah. And your transformation, even your output transformation, like if your output transformation has N or an M, it's going to be based on the original input to A as well. So they typically line up.
They may
Like just give
differ,
the
but
runtimes,
it's still...
give the runtimes in terms of problem A.
Okay. And I have another question regarding the choice of the problem A you want to reduce to B. So we have those kind of search problem in terms of the budget and the target. And sometimes I see that they say that they formalize the problem as the number should be less than or equal to the budget or greater than or equal to the target. Or sometimes I see that they say that the number equals the budget or equals the target. Are we accept? Can we use both versions, or it must be one of them when we try to select a non-NP complete problem?
I usually use the less than or greater than, less than or equal to or greater than equal to 1, because then I don't have to deal with it. And it'll be evident in the way you write it. Like it's not something we nitpick over. I'm trying to think if there is a yeah, you can feel free to, and I actually suggest this, use the inequality version. It's easier.
Let me see. So if you are trying to solve some A that is less than or equal to B, and the problem you reduce it, because sometimes when they when they state the problem, they say that the problem is strictly equal. So I mean the NP complete problem, we know they are stated in this inequality way, but the problem we want to solve are stated in the exact equal sign. So when you try to reduce from A to B, and if A does not have, if B does not have an exact solution equal to the budget B, but if you reduce the budget, maybe you can find it.
I would just use whichever version you think is useful. So like every single one of these NP hard problems have various like different ways to do it. There's the decision problem, which is just yes or no if it has an answer. There's the optimization one, which is get the max with the num, and then there's the equality versions, which is find something with exactly G or exactly K, and then there's generally an inequality version, which is less than or equal to G or greater than or equal to K or stuff like that. I would say you would just go with the one that makes the most sense for the problem you are trying to prove. And some students will state the inputs to their known problem. That's perfectly fine. The inputs and outputs to the known problem. That's perfectly fine. Or you can just imply then, when you return a valid solution, whether it's a equality version or an inequality version, it'll generally just line up, and the graders will figure it out. I will say that you want to pay attention to the problem statement of problem B. That's more important, but the problem that you pick can be of whichever version works for your solution.
Got it. Thank you.
Yep. All right, we'll move on. All right, so then this is the final part of it, is that you have to actually explain why your reduction works. And so this show B has a solution if and only if A has a solution. So there are multiple ways to do this. You can say if A has a solution, then B has a solution, and if B has a solution, then A has a solution. This is the standard both positive implication. The other thing you can do is if A has a solution, B has a solution, and if A has no solution, then B has no solution. So what this does is it swaps the second one for a contrapositive. If B has no solution, then A has no solution, and if B has a solution, then A has a solution. This swaps the first positive implication also for a contrapositive by keeping the second one, and then you can do swap both. And I don't suggest this one. This one is extremely confusing to write. It's also extremely confusing to read. So even if you write this correctly, your grader is almost is more likely to make a mistake in the grading, and you'll have to do a regrade feedback. I really don't suggest this one. I suggest just picking one. Some students will say, how do you know which one to do? I just pick one. I think once you get like really used to writing NP reductions, some of them will be easier on some problems than other. But for starting up and in an exam setting, I would just pick one. I do like this one quite a bit. I say that if A has a solution, B has a solution. If B has a solution, A has a solution. I'm also pretty, I like B quite a bit too. So A has a solution, B has a solution, A has no solution, B has no solution. I don't like C. I hate D. So those are my rankings. I would rank A and B about the same. C if you feel really comfortable with it. D, you're gonna run into issues. Try not to do that one. So yeah, just pick one. And if you mix some of these accidentally, what you end up doing, unfortunately, is you end up arguing one direction, and then you take the contrapositive of that and you argue that direction a second time. And if you do that, you're going to miss one of the directions of the if and only if. What you have proven then is if A, then B, and then if A, then B again. And so that's not good. That's not a equivalent. And so what you could end up doing is like if you say, let's see, if A has a solution and B has a solution, and then you say if B has no solution, then A has no solution, then you basically just argue the same thing twice, and that would be unfortunate. Okay. All right.
Can I ask a question here? So if you go with A, can we swap around if B has a solution and then A has a solution, and then if A has a solution and B has a solution? They're both equivalent, right? So
Wait,
just
say that again.
For A, if we go in the way, if you first say if B has a solution, then A has a solution, and then we prove if A has a solution, then B has a solution.
Yeah, the order of these two, the order of these two don't matter. As long as both statements are given, then given and proven, then you're good. It doesn't matter if you do this one first or this one first. Like the order of these two don't matter. I tend to do A to B, but if you wanted to do B to A, you can swap these two. That's fine.
Okay. And one other thing is that oftentimes when I'm writing the correctness, I feel like I'm repeating whatever I did in the input-output transformation. How exactly do these differ from that?
So it depends on your writing style. Some students, when they are writing the transformation, they'll feel the urge to explain why they're doing the transformation. And then you're correct. Sometimes when you write the transformation and you feel the urge to explain it, you're kind of writing the correctness into it. And then after that, you're writing a more formal statement of correctness. Of like the way I write my solutions, when I'm writing my transformations, I just tell you what the transformation is, and I don't explain why I do it at all. Then in my correctness, I argue my correctness, and that's where I explain why I do certain things, why it works, and why those are that's correct. So it depends on your writing style. Like I said, you can't really lose points for writing too much, with the exception if you write too much and you write something wrong, and it's contradictory. You will lose points. A student has asked, we only need one of these statements correct. And that is correct. You only need one of these. Yeah, only one. Yep. Okay.
Thanks.
Basically, to prove NP hard, you just skip the first step, proving that it's NP, but the rest is the same, right?
Yes.
Got it.
And sometimes, and that happens, right? The standard, and again, like I said, there's always different versions of all these problems, but like the standard knapsack problem is considered NP hard. How do you know that what you have chosen are the best items to include in your knapsack? The only real way to prove it is to redo the algorithm, right? Like there's no way to like prove that is the right solution unless you rerun the algorithm, and therefore that's an NPR problem. And that typically is an optimization thing. Like if you're looking for what is the best value you can get in a knapsack, then the optimization version of that problem is typically NP hard, not NP complete. But if you were to say, can I get a value of 100 given this budget and these items, that becomes a what's the word?
Search problem.
Search problem. Yeah, you're searching for a solution that fits the requirements, and search problems tends to be NP complete.
Optimization is not always NP hard. For example, if the number you can do binary search, like the smallest number.
I mean, there's those exceptions to this. This is just like a general statement. And the actual thing to say is that unfortunately they are all NP hard. It's not that it's not NP hard. It's not. It may or may not be NP complete.
That's correct.
The really annoying thing to me is that there's a word to say NP hard. There's a word to say NP complete. I don't know of a word that says NP hard but not NP complete. So it's annoying. NP complete is a subset of NP hard. That is correct. All right. Moving on.
I had a question on this real quick before we move on. So here you have, if like for the first one, if A has a solution, then B has a solution. But I was looking at the ed post on how to write an NP proof, and they have for the first one, if B has a solution, then A has a solution. Is that direction interchangeable?
Let me see what that looks like. What's the name of the post?
How to write an NP proof. It's one of the pinned ones.
I should know this because I think I wrote most of this. B as a solution, A as a solution. If A has a solution, yeah, it's just the reverse of what I said. It's the like I said, the order. The very first one is the exact same thing. The ordering is just flipped. It doesn't matter.
Okay, so you can say A then B or B then A.
Yeah, I always do A then B. It's just easier on my head. In my head, but like I said, pick the one that is best for you. There is no best one, except for whatever you can remember and prove consistently.
Okay.
Yep. All right. Things to watch out for. Going in the wrong direction, unknown to known. Don't do that. Trying to describe how the unknown works. Trying to give me an algorithm of how the unknown problem works. Don't do that. We don't know and we don't care. Like, it's not required for this proof. And one, you're going to get into trouble. Two, you're going to lose a lot of time. And three, you're almost always certainly going to be wrong on that solution. These solutions are hard, right? That's the whole point. Like, these are hard problems to try to prove. So don't do that. Solving some part of A before using B. So like if A has a click problem, and then we attach something to the click, you can't do this because you can't find the click. Okay. Finding this click to attach to would already be non-polynomial. Assuming that A has a solution, you shouldn't assume that the input to the click problem has a click in it already, because we don't know. Because this constrains the input to A, which is not allowed. Not transforming the solution to B as a solution to A is a common problem. So even if the solution is exactly the same, sometimes this happens from SAT to SAT. You get back the exact assignments that would solve the first problem A. You still have to say return my assignments as the assignments for SAT. Like, you have to make that statement. That statement has to be explicit, or you have skipped the entire output transformation and you're going to lose points. Not giving runtimes in Big O. So, that's a mistake. If you say this is polynomial, you're going to lose points. And it needs to be stated even if there's no transformation. So if you say something like, I'm just going to take my output to B and return it as my output to A, this takes all of one. You still have to give that runtime. You cannot skip the runtime. It's not going to be assumed for you. You're going to lose points. Okay, so be careful there. All right. So this is the strategies that I tend to use when I go through the different types of reductions. I think someone was asking, like, how do I approach these? These are kind of things that I look out for, things I consider as I'm trying to solve the problem. And then, if it doesn't work, I move on to the next one, and hopefully I find one in time. So if you're going from, have you guys seen exact 4SAT? Was that a practice problem for you?
Yes.
All right, great. So if you're going from 3 set to exact 4 set, or set to stingy set, did you do stingy set?
That's one of the problems that asked for your in your office hour.
Great. So any of these set reductions is from basically you're taking one of the more general set problem, 3 set and set, and you're going into a more restrictive or a slightly altered version of set. So exact 4 set, stingy set are more restrictive versions of, say, a set or 3 set. Okay, so this is like how set reductions tends to work. So for the NP proof part, what you have to watch out for is that you have to make sure to verify the set assignments. So if you have an exact 4 set or a stingy set, you have to make sure that each clause is satisfied given the assignments that you have. You have to state that. Make sure to count anything. So if what is stingy set? Let me see. Stingy set, the one I'm thinking of.
I believe stingy set is the one that requires k amount of true.
All right. So if you're looking for at least k variables that are true, right? You have to count how many variables are true. You can't just assume that you have k variables, right? So anytime you're given a g, b, or k, you have to verify that g, b, or k is met. Anytime you have a verified a set assignment, you have to verify that your clauses are satisfied. Okay, so those are your 2 big things for NP proof. Make sure to verify any special conditions in the solution. You don't have to verify the input, so you can assume that the input is valid, but if you have special conditions, like you have X number of true assignments, you have to verify that there are X number of true assignments. Those are like special conditions in the solution. Input. Be sure to maintain the CNF format. So CNF format is a clause with a bunch of or statements of literals, and another clause of a bunch of or literals. Okay, you have to make sure that you can maintain that CNF. You cannot put like an and in the middle of a clause. You cannot put an or between 2 clauses. You have to maintain CNF. Otherwise, these aren't proper set inputs. Be sure to maintain the equivalent logic. Do not alter the logic of your original CNF from the known problem. If you mess with it too much or like without careful consideration, you end up with a solution to one of these problems that doesn't match the solution to your original problem. Like you'll get the wrong answer basically, and that's a big penalty. So equivalent logic is very important in stats. Be sure to only add literals and clauses. Don't add anything weird. Don't add something set to true. Don't add something set to false, right? You can only add literals and clauses because that's the only thing that CNFs are valid for. Never add a true or false because that's illegal. So like sometimes you get a problem like, you get at least one true clause. And some students will be like, oh, I'll just add a clause that is set to true and therefore it'll be true. And that's not okay. You can't set something to, you can force a clause to evaluate to true or false, but you can't actually set it to true or false. Output.
So would it be valid to add a condition to every clause, like add a literal to every clause?
Yeah, that's allowed. You can add anything to any of the clauses as long as it's valid and it does what you need it to do.
Okay.
Okay. Remove the added literals or variables. When you get a return statement from a SAT problem, it's going to be like A is set to false, B is set to true, C is set to false. If you added like a variable D that the original problem doesn't know, and then the output is set, D is set to true, it's not a valid output for your original SAT anymore. It makes no sense, right? That D has no meaning to your original problem input. So you have to remove any literals or variables. Okay. Don't bother removing clauses or thinking that removing the added clauses is what you need to do, because the clauses are not part of the output. So like if I did something like add a clause such as I have y in it, right? I now, on my output transformation, I have to say remove the variable y from the solution. I cannot say remove the clause that I added. If I remove this clause, which was part of the input, the output doesn't actually have this thing, and then y is still actually returned, and then your output transformation is still wrong. Okay, you have to remove the literals or variables that you've added, not the clauses. On the correctness, what I kind of like to do is you can try to establish the equivalency of the two SAT problems after the transformation, and then you can argue the if and only if a little bit more simply. So like if I said, I've added these things that make my my exact 4 SAT problem logically equivalent to my 3 SAT problem. Therefore, if 3 SAT has a solution, exact 4 SAT has a solution, and if exact 4 SAT has a solution, 3 SAT has a solution. I've argued the equivalency of the input and output transformation in one part, and then I just restate the if and only if. That is something that is somewhat unique to SAT reductions because it's a very logic-based problem. So that's what I like to do. You don't have to do it that way. If you're uncomfortable with it, feel free to do one direction at a time. That's fine. Question?
Hey, sorry, I just wanted to clarify, make sure I understand. So the output for a SAT problem is just going to be all of the literals with a satisfying assignment. All right, so let's say you had some C and F that had literals A, B, and C in some set of clauses. The output to SAT will simply be
Yeah, I mean you can make it it's kind of abstract, so you can kind of say it in any way you want. So like one way to consider it is that you can say, if you have A, B, C, one way to look at it is that this is what it returns. Another way to look at it is that you get returned all the true assignments. So it could be that like you get returned A, which is set to true, and then because B is set to false, then not B is one of the things that get returned, and then C gets returned. Like either way of these, like just kind of make it clear in your statement. Generally, it won't matter. Generally, if you're going from SAT to SAT, you can just say return the assignments, and that output just kind of like carries over. But if for whatever reason you're crossing domains and these kind of things matter, you can just make the statement of like, this is the version of the SAT that I'm using returns, and this is how I'm going to use it.
Sure. I just want to make sure for sake of understanding. Thank you.
No.
Quick questions. MP proves the runtime for exact 4 SAT stingy SAT that will be n multiplied by m, n variable and m clauses, or is n squared? The runtime.
The runtime for this?
Yeah.
For this one, hold on. Wait, can I erase? Does this erase? No. Okay, I can only, okay. So for SAT, the verification for SAT is n times m. And the reason for that is that you have n clauses and it could have up to n variables. So that is your verification run. For 3 SAT, it is O of m. Because each clause can only have 3 being a constant, your runtime is O of 3m, drop 3, you get O of m. So these are the runtimes for verification steps.
Okay, thank you.
All right. All right, we good? Moving on. All right, so graph reductions. This is a different domain, different class. These comes in the format of the independent set. You click plus independent set or click to subgraph isomorphism. So the NP proof, what you should watch out for is that make sure to verify the graph carefully. SAT is actually very easy to verify. There's only a few steps. There's only a few things you have to say. Graphs are actually much more difficult because graphs you have to verify all the different parts. Like I'm sure the Spider-Verse with the spider, it was not like, oh, just verify that it's a spider. It was like very thing. So if the graph contains a click but isn't separated, you have to separate it first. You have to isolate what you want to verify as a click. If you were given a possible solution to a problem and you don't know what that solution looks like, and you say verify that as a k-size click, that is basically saying find a click in an unknown graph, and that is not okay. That is not going to be a polynomial step. What you have to do is that if you know that you are looking for a k-size click, right? I don't know why I'm bothering writing this down. Isolate all the vertices. That is k minus 1 degrees. Okay. Right. So that's a polynomial step. Now you have isolated this k minus 1 set of degrees, and then verify if they are connected to each other. And that is how you find the k size click. Okay. Now some of them might not all be k minus 1. Like if you had a spider with that extra leg, it's actually k degrees, right? Like so make sure you isolate what is a possible candidate click and then verify the click. Do not just search for the click arbitrarily in your solution candidate. Okay. Finding a click in an arbitrary graph is not polynomial. That's what I just said. Make sure to count anything or check the size of the solutions. A lot of students skip this step. Like, if you're looking for a k-size click, you have to verify that the click that you're verifying is actually k-size, right? You can't just assume that. Try to avoid degree counting, which is usually wrong or is much harder. Now, when I say degree counting, I mean like, some students will say, verify that there are k number of k minus 1 degrees. Verify that there is, 2 k degree vertices. Verify that there's 1 k plus 1 degree vertice. Like this is like a degree counting. And we had a student that we are good friends with now that's just sits around and messes up these verifications. He is very, very good at finding these like weird looking graphs that will fit all these requirements and not be the graph you're looking for. So this is almost always going to be wrong. So what you want to do is just isolate your click, verify that it's a click, verify all the other different parts to it. It's a much easier way to do it, and there's very few chances of errors doing it that way. Don't do this. This is bad. Don't do that. For the input, oops.
All right, so you're basically saying we should perform 2 steps: find the degree, the vertices which satisfy a certain degree count, and then find a click within those vertices.
Use degree counts to isolate the part of the graph you're trying to verify, and then verify it. Don't just rely on degree count. It's very unreliable. People always make mistakes. I always think that I'm being very, very smart by doing it, and then I always get pointed out that I made a mistake. So I don't do that anymore. I used to think like, oh man, I'm so smart, I can just count degrees in this, and then the guy that I told you, my friend, he'll just draw a graph and make me feel bad about myself. So I don't do that at all anymore.
Okay, gotcha. One more thing, maybe we'll go through this in the solutions, but the runtime for finding degrees, that was also a bit disputed in homework 7, because
finding degrees of a graph, all of n squared, all of n times m, one of those. Right, at each vertex, you're counting how many oh no, so all of n plus m. Sorry, I take that all back. All of n plus m.
In homework 7, I was penalized saying that finding a 1 degree node should be O of n.
A 1 degree node should be O of n. I don't know what your solution looks like, so I don't want to And generally, I think to find a 1 degree node can be O of n, correct?
Mm-hmm. It can be, but it can also be worse than that, right?
Yeah, but again, like if you give like about like a general like one checking the degree of a graph is every single node in the graph is O of n plus m. It's easy to find a very specific number. One time is O of n. Yeah. Okay.
All right.
All right. So on the sorry, I have one person with hand up.
Yeah, questions on NP proof. If we are checking anything like independent set, click, and vertex cover, we want to verify the size of that set, right? The two vertical bar and the S is at least, no, not at least, but yeah, at least B, right? Or either B or G is at least B for budget and no, at most B and then at least G for gold. That's what we want. That's what we want to prove. Yeah. Yep.
Well, hold on. If I hit Control Z, what happens? Nope, doesn't do anything. Okay. Yeah, like sorry, B budget. This is that one. You want to verify that is what T K K greater than equal to K.
K would be the goal and
and right. And so this is okay. So this is what I'm talking about. What you can technically say, if you really wanted to, is that this is O of K, where K is less than equal to n. Okay. So what I'm saying right now is that I'm going to give it O of K. K is a magnitude, technically pseudo polynomial. However, I know that K is less than equal to n for the problem to make sense. Therefore, I have bound this K to this n, which is an input, and therefore this is now a polynomial. Okay. Or more easily, I can just say this is O of n, and I'm done. I don't have to do all this. I can just do this. But if you do O of K, you must say that K is less than equal to n in order to bind it to an input size. Without binding it to an input size, this alone is considered pseudo polynomial, and you'll lose points. Okay.
Thank you.
So the input, do not try to find what you're looking for before modifying it. Do not try to find a click before you add legs to get your spider, because finding that click is not polynomial. Don't do that. Force your unknown problem to find the solution for you. You always have to make it so that the unknown problem does the finding of your click, not you finding the click and trying to do something. Graph reductions, I feel, are a little bit trickier, so you have to be a little bit careful there. Remember to set your B, K, or G. Graph problems tend to have a auxiliary requirement of some budget, some target, some goal. So remember to set it, even if K equals K. Okay, even if your spider of size K click is exact same K as the K of your click problem, you have to set it. Okay, you have to explicitly state it. Okay. Be mindful of accidentally adding extra candidate vertices or edges. You don't want to accidentally alter the original graph such that you create a K+1 click. And that's what I think that's one of the things that we put into the formatting quiz, the NP complete quiz, is that one of the solutions, what you ended up doing is I forget which one it is exactly. Either IS or click the alternate solution, and then you end up with a K+1 because you end up adding an extra point that could be part of the independent set. So you have to look for a bigger independent set. So be careful of doing stuff like that. Output transformation. Again, isolate the thing you're looking for from the unknown output. If you get a spider back, you want to isolate the click to be returned. Again, you can't just say return the click. You have to isolate it. There are some problems where it divides the two things into sets. So I believe the IS plus click solution is a set of independent set vertices and a set of click vertices. And in that case, the click is already isolated and you can just return the click. For spider, if the spider is returned to you with a click plus a bunch of legs, you don't know which vertices are considered the click. So you have to find it in your output. Similarly to how you had to first isolate the candidate and then return it. I think for spider, you can basically return everything that has greater than 1 degree. I don't know the exact wording of the problem, but that's probably something you would likely do because all the legs are 1 degree, I think, right? So if you return all the vertices that's greater than 1 degree, then you have the proper click.
Actually, this is one of my questions. So in the Spider-Verse, if you do with a big G, then you can claim this because the degrees, they are clearly separated. But if for some corner case like G equals 1 or G equals 2, then you don't necessarily have this condition that the degree, small degree are not the decay part. So my question is, when we work on this kind of problem, can we ignore the corner case? Because if you want to prove some problem is NP complete, the small g doesn't matter. Only the large G make the problem difficult, right?
I have fought tooth and nail for you guys on stuff like this. I have had to argue with students and argue with other TAs. It will not matter. You do not have to isolate very special cases of the problem such that you have to like go out of your way. Yes, if a spider comes back with a single is a click of 1, like don't worry about it. Just don't consider that like very niche case. Just write your solutions for a general K that's big enough that you don't have to give special reasoning.
That's great. Thank you.
Yep. Yeah. I will add an additional note. Remember how I said you can't change the input to your original your problem? There is a slight caveat to that, in that you can do some shortcutting of well-established transformations. For example, if you're doing FORSAT and you don't want to write all the different expansions of a single literal, because a single literal, I think I've you should have seen for that, has a big expansion. What you can do is that given a initial problem to say SAT, you can say, assuming that the SAT input is has no single literals, because you could just eliminate them such that they're already gone. We work with a input of two or more literals. That's okay, because even if you did have a single literal CNF in your transformation step, you would simplify that to a non-single literal CNF and then put that through your exact FORSAT using these. So that's okay. Does that make sense? It's like a slight tweak on what I said. Okay. Moving on. Reductions.
Question for the output. I guess, should we just like not consider anything we did as the input to something we know in the output transformation? Like we can't, for spider, for example, if we add a bunch of legs, we can't just say remove any of the vertices we added. We actually have to go through and verify that those are all degree 1.
Yeah, so 2 parts to that answer, to that question is, 1, you do have access to all the things you did in your input. Your output transformation is based on the knowledge that you have from your input transformation. So that's important in some cases. Like in the SAT transformations, you do know which literals you've added. So when you go remove those literals, you can say remove all added literals. So that's important. You have access to that. However, and that's the thing I'm about to get to you now. Just removing the added vertices or edges is not quite going to work for graphs because of like you do have access to them, but removing them isn't gonna always work, and I'll explain why in a second. So suppose I want to say, let's make a small spider, right? And I go, okay, I'm gonna add one leg to each, to each vertex, and that's my spider, right? And then when I get, when I put it into my spider black box, I get back the spider and I go, okay, remove all the vertices I have added. And so I'll go, okay, I chop off this one, I chop off this one, I chop off this one, I chop off this one. Cool. I now have my click that I want to return for my problem. And you're thinking, yeah, that's how we would do it. However, what can happen is that the original input that you have might already have this spider, right? It could already have the spider just by happenstance, right? Like the spider already exists, right? And what you end up going to do is you're going to add additional legs. You're going to add all these additional legs, okay? Okay, so I've added all these additional legs to the spider that exists. When you put this into your Spider-Verse, there is no sense of saying, oh, pick my leg if you can, and don't pick the leg that's originally in. So what it might do is it might just return these original legs. And then when you return those original legs that was originally in your graph and you go, okay, remove all my vertices, those original legs that was found in your as part of your spider in the original graph is still going to get returned. And now you have a broken click and it's not actually a click and you busted your output transformation. So I would say on the SAT transformations, you generally can just remove the added literals and variables. On the graph transformation, you have to be much more careful on the output transformation, not to just remove those. You have to actually carefully remove the things that don't make up whatever your original problem is.
Okay, that makes sense. Thanks.
All right, moving on. Correctness. Argue why the solution for the unknown can only be found if the original G has a solution to your known. Yeah, so this is B has a solution if A has a solution, and then vice versa. Oh, yeah. Did I just like lose one? Okay. Let me edit this live. Why? All right. All right. There you go. So argue both directions. Make sure. Okay. So set reductions. I think you had this one recently. Right. This is the one with your neighborhood one. I think that was a set reduction. So vertex. Did you guys have hitting set? Is that one of the problems I had to go over?
Yes, please.
Yeah, hitting sets on the list, but we didn't. We arguably did or did not have a set reduction as a homework.
All right.
It could have also
depending
been
on.
So
yeah, could have been vertex cover, and it works out because vertex cover and set cover actually reduce to each other pretty well. Okay, so vertex cover to hitting set, which is probably what I'll end up doing. So the NB proof, make sure to verify each set and its content or intersects. So basically just verify the restrictions or the requirements. Make sure to count anything or check the size of sets. So you have given some case number of sets that you can use. Make sure you count and then verify that it fits under that number. Consider runtimes as how large the largest set can be, usually size of all allowed items. So when students are asking like, what is the runtime for this, for these kind of things, if you have m sets, okay, you can define n to be the number of unique items in your sets. Okay. This is generally given to you. This is sometimes given to you, but not always. But you can discover what n is based on your input pretty easily. And this is one of those instances which is kind of weird, is that if this is not like provided to you or known to you, it's still based on your size of your input. So you can define this yourself and say, given that n is the number of unique items in my set problem, my runtime is all of m times n, right? Because it's kind of like, it's almost kind of like a verifying a set, right? You have m sets, and you want to find out how many if those items are. I think the most naive runtime is O of m times n times n, so O of m n squared. This is like the naive runtime that I would use. I have like a faster runtime, but this is the one you should try to remember, because you're going to go through each set, which has a maximum of n items, and you're going to verify against a intercept or a kind of thing. Okay. Limited time validation for Joves. I don't know what that means. What's wrong, Jamie? Why are you looking suspicious? What's happened?
People making some strange comments.
Oh, okay.
we do have the question from Rohan. So if we do use this kind of declaration of n being the number of unique items, do we have to include the runtime of determining that set? Right, which I guess would just be O of m, but
I think for set cover, you are given the entire set of items. So it's an input. You don't need to spend time to determine the n.
Okay. I mean, yeah, if it's given to you, then it's fine. I would think that, like, given a set cover problem A, m and n are given to you. So I feel comfortable with that. How about you, Jamie? Does that sound okay?
I had to add it because Dr. Brito did not add it to begin with. I figured it would make sense just to give the students n.
Thank you, Jamie. We appreciate it.
While Jamie's here, I do have a question.
Thank you.
Is Jamie the guy that's good at finding those graphs you described?
No. The person that I'm talking about is not a TA. We just hand him some, and then he draws me a graph that says no. And I basically stopped doing that because I thought I was really clever, and I'm not. So we no longer do that.
The quantity you wrote here, m n squared, that's the runtime to check that, to validate a set is a hitting set, right?
Yeah, hitting set or intercepts in general.
So basically, for each item you check for each set, and for one of these m sets, you run through these m sets to see that if it coincides with one of its elements. So that's m times n, and you want to verify it is in this set. Let me see. Why it's n times n squared?
So you have these sets.
Oh, I see. The candidate solution has n elements. Yeah. For each element, you run through n sets, and in each set, you go through n elements again. Okay, got it. Thank you.
All right. So then on the input, so you're allowed previous set problems. So hitting set, if it's covered, you get to have it set covered. You should also have that. Also from graph or sat, be careful with sat as literals are related. So a lot of students will make the mistake that they'll just convert a vertex set, a set cover to a sat problem. But the individual items in a set cover are not related to each other, but the individual literals of a set are related to each other, right? They have to be, in one clause, they might be set one way and the opposite has to be set another way. So it's actually very difficult to go from this. So be careful there. Don't try that too many times, unless you're very comfortable with it. Usually it's considered a generalization problem, that is create an equivalent problem to be solved. And again, a generalization problem just means to give the step to make two problems equivalent, and then it's easier to argue the if and only if. But you don't want to write it that way, because on the exam you're going to be expected to write like the full piece by piece. Consider runtimes and how large a larger set can be. I already said that. Oh yeah, similar to the NP proof. And then output, be careful to convert back to the thing you were looking for. Of all problems, set reductions tends to be the one that crosses domain, like from graph to sets, or from graph to sets or sets to graphs. So you have to convert it back to what you're looking for. I believe this is can be what your Computopia problem was like, where if you use set cover, you'd have to be careful to sorry, let me take that back. If you went from vertex cover to the Computopia problem, the Computopia problem is set up as a set problem. And so you're going from graph to set, and then when you convert back, you're going from set to graph. So you have to be careful that you're converting back and forth between what you're looking for. And then the correctness, argue why the problems are equivalent, then argue the if and only if. So this is also kind of like a thing where I said, in SAT, if you wanted to be more concise, you can argue that the two problems are equivalent, and then argue the if and only if from there. Or you can just do one direction at a time, perfectly allowed. Pick whichever you're more comfortable with. Summation reductions. This is another one that that you should see in your lectures in your book. So subset sum to knapsack is the classic one. And so with the proof, it's a generally straightforward to verify. Summation reductions are probably the easiest to verify, because you're just adding up numbers and making sure that they total to what you expect. And knapsack is kind of in that summation category. Does the solution set add up to what we are looking for? Remember, adding is O of n log x, where x is the sum of what you're adding. So when you are verifying, and this is why verifying a given b or a given c is considered to be polynomial, even though this is a magnitude, and we said that working with magnitudes directly can be considered pseudo polynomial. When I want to add up to b, we are doing the number of bits. So b at b is represented in log of x, right? The log of b, that's the number of bits that b is. And then if I want to add up to n possible values of this representation, then the runtime is all m n times log b, and that is a polynomial step, and therefore it is verifiable in polynomial. Because remember, I said when you take the log of some magnitude, you have taken the exponential or pseudo polynomial number and you brought it down to the polynomial level. Input 4 sums to represent the solution. So you want to try to make whatever you're looking for to be equivalent to the summation of your known problem. Consider bit or integer representations, and I think that's what. What's the other problem that's not sum? The ones and zeros problems, or 0 or 1? I always forget what that thing is called.
COE, 0 or 1 equation.
Yeah, 0, 1. So like a 0, 1. What was that reduced to? It's covered in the book. I don't remember. I think it's like 0, 0, 1 was reduced to subset sum. And so what it does is that it takes the 0, 1, creates a bit representation, and then turns it into a subset sum problem. It's a really neat reduction. It takes a lot of intuition and leap of faith to sort of fully understand it. It's something I suggest you sort of try to understand without having to be like, oh, I definitely know how to do this. I think that level of difficulty is above and beyond what we expect for the exam, but it is kind of a really cool reduction to see how we go from one representation to another. Consider forcing inequalities to converge on to inequality, and that's how knapsack works. To go from sum to knapsack, we turn the inequalities of the less than equal to b greater than equal to some target, and we set this to the same so that it becomes a singular sum from the subset sum reduction. So that's how you want to approach it. Do a convergence, and then output, be sure to convert back to the thing you were looking for. This is true for all output transformations, but it's especially important for set reductions and summation reductions because they tend not to represent what you are starting with. And then on the correctness, argue why the summations are equivalent, then argue the if and only if. Okay. And then, so the reductions that cross domains, these are gone over in the lectures and in the book. So if you want to go from, say, 3 set to independent set, from 3 set to subset sum, 3-dimensional matching to 0-1 equations. I think these are all in the book. So on NP proof, this is generally going to be the easiest part because you know what you're looking for. And in general, I think the NP proof, as long as you're not like overlooking things, it's to me a free 4 points. Like you should not, as long as you write down all the requirements that the problem is asking, just verifying them and being careful and being diligent about it is how you get those 4 points. There's not too much trickery in the NP proof part. And then for the input transformation, you basically just pray and hope you get it right. Same with output transformations. You just basically hope that you say the right words that the TAs are okay with. And the correctness, you do the same thing. But in all seriousness, you're not going to get this kind of problem. This is considered way too hard for exams. This took like, PhD and like, super famous computer scientists to do these kind of reductions. I think it's fun to read and sort of like understand the very difficult approaches to this, but you're not going to get something this difficult. We don't assign these as practice. We don't assign these as homework problems. It would be very unfair. I wouldn't know how to do it. And so I would fail along with you guys. Okay. Jamie's kidding, hopefully. All right.
There's no way we would do it on the exam. 100%.
Yeah. I would go to battle for you guys. If I saw this on the exam, I was like, no, Dr. Brittle, that's really mean and unfair. I don't think you should. Although I'm not technically a TA this semester, so all the problems you guys have been seeing, I haven't had like a preview of. So yeah, if they've been too hard, then that's not my fault. Not this time. All right. Linear programming. I said I would talk about it a little bit. I'm not really going to go over it. It's math. Like I know this is like a cop out, but like in general for me, and you haven't done RSA, you haven't done FFT, but you will have linear programming. To me, these topics are just math, and I don't enjoy them because I don't think that there's like any sort of like cleverness or like any figuring out of this. You're just basically presented an equation that you have to get the solution to, and so all it is just practice. Great. So remember the requirements, remember what the restrictions and constraints of linear programming is, remember what you have to do to make a proper linear programming equation, remember the parts and what they mean, what is the constraints, what are the target, what is the function called? The target objective functions are what they mean. Remember what the standard form looks like. See Emily's LP guidance on this. She has made an excellent post. We've shared that post over several semesters, and students have always learned from there. So make sure if you haven't read this, you're really doing yourself a disservice. And then remember how to get the duals, how to get from one to the other, what the duals mean for the primal and stuff like that. Remember the feasibility and boundness rules. There should be some like nice little chart that's being posted on like if it's feasible and if it's bounded then that means this. If it's not bounded and stuff like that, I don't really remember them. So make sure you remember them. And then remember to do arithmetic. Seriously, I think sadly, this is probably where a lot of students end up losing points. Like I've seen people do like, 5 minus 2 equals 6, or like, something really silly. And like, their brain is all clouded from all the NP complete problems, and they just forget how to do simple math. So double check your math and be careful. That's it. And then these are not hard, but they require understanding, they require practice. And again, it's just math. It's math. There's not much more you can learn other than just practice and remembering all the different rules. I myself am not a big fan of math classes. I hope that that's probably abundantly clear. I've never enjoyed like the math classes too much. Okay. So about 7 minutes before 3, I'm going to go over some of the common mistakes of homework 7 and homework 8. Then we'll take a break, and then I will go over some of the practice problems that we talked about. So the most common mistakes in homework 7, establishing runtimes on G or K without binding it is about 10% of students do this. Remember, this is considered a pseudo polynomial. This is not without binding it. It is not considered a polynomial step. In the NP proof section, 40% of you did not induce a subgraph in order to do your verification. The requirements of the problem is to get an induced subgraph, and then here are the things that you have to verify. If you don't get an induced subgraph as your first step, what you're verifying against is the full or partial graph, and it's not the induced subgraph, and so therefore that's a mistake. Not checking the size of the spider. If you're given some kind of constraint on the size, the budget, the goal, you have to verify that, okay? Does not isolate click candidate before verifying the click, and that's what I was talking about. If you're just looking for the click in an arbitrary graph, because you don't know if it's a valid solution, you just have an arbitrary graph and it says, is this a solution? And then you go looking for a click, like, without first trying to isolate it, it's not going to be it's not going to be polynomial. It's going to be unfortunate. Okay. Runtime analysis is incorrect or it fails to establish polynomial time. 15%. I think this number goes down as we go through the homeworks and we get to the exam, which is good. I think what students end up doing is that they see this post about it doesn't matter how slow your runtimes are, and they mistakenly think that means runtime no longer matters, which is not the case. Your runtime still matter. It still has to be accurate. It still has to represent what you wrote. It's just that if you did something in O of n squared versus something in O of n cubed, we don't care because it's still polynomial. But if you write O of n squared, you have to, it has to match what you're doing. Otherwise, a student can say, oh, this all takes O of n to the 8th. Whatever they wrote is probably faster than O of n to the 8th. But without it actually like being tied to what they did, you're not going to get points for that, right? So be careful with that. Input, big mistake is not set or set wrong G. Oh yeah, this G for Spider-Verse is I think the problem is set up so that G equals K. If I remember this problem correctly. And if you just assume that this K comes along with you from your click problem, that's not correct. You have to set it. Even if it's K equals K, you have to set it. You have to explicitly set every single input of your problem B or unknown problem. Okay. Does not add n legs to G to induce a spider. This is the core concept of this problem, is that if you didn't know where the click was and you wanted to turn any possible click into a spider, you add a leg to every single vertex in the original graph. That way, if there is a click, it'll have the legs needed to be a spider. If there isn't a click, adding those legs will not create a click needed. So it's okay. So you can't say find the click and add the legs. You can't say add the legs to k random vertices, because those random vertices might not create a click. So the key concept of this problem is, let me add a leg to every single vertex such that if there's a click, I will have created a spider that is that click plus the required legs. Okay? All right.
Sorry, but you don't have to say in the transformation that such that if there's a click, then there's a spider. You can defer that for the correctness, right?
Yes, you can defer that for the correctness. I'm just explaining to why this right here is the core concept to this problem.
Okay, got it.
Yeah. Runtime analysis incorrect replaces the established polynomial time. It's about the same as the NP proof. Again, students tend to be a little bit too relaxed with the polynomial runtime. It's actually really interesting. And this is not something that like I feel like the class does a poor job of telling students, because I think students just their innate behavior is you start off with bad runtimes in the early topics, and then you get better and better at them to the point where graphs tend to have pretty good runtimes. And then you get into this NP complete, and students are like, oh, I don't care anymore. And then that spike in wrong runtime goes back up. And then on the next homework, when students realize, oh, it does matter, it actually matter, it comes back down. And by the exam, it's all generally pretty good. So these are kind of predictable. And that's just how students I guess learn and relearn certain topics in the class.
Hi, Joves.
Yep.
How are you? Yeah, I have a question about to establish polynomial time for for input or output transformations. So it's very interesting because, for example, right, if I to remove the leg of the spider, I mentioned this n square. Because we have the the out loop and the in loop, but I have similar kind of situation. Here, say I use the pseudocode. So if I to establish n square, how do you think I can avoid this kind of tricky description to verify this n square for separation of the
the legs, to remove the legs from the click?
Yeah, the leg from the spider, remove the leg, right? Remaining at the click. Also,
I don't think it would be O of n squared. It should be O of n, right? To remove the legs. Why would it be O of n squared?
Because I don't know. The edge is adjacency list for this graph.
So I think
for
that's
example,
fair, right? Like you told me that it's O of n squared, and I asked you why is it O of n squared, and you said I don't know, and therefore I think there's a penalty there, because it's not the
So this is very similar to the to the click, right? We had to iterate every pair of the vertex.
Yeah, but you're
to check whether they are connected. So similar.
Right. So
I check every pair of the vertex to see if there's only one connection for the other vertex. So that's why n square. This is inner loop and outer loop, inner loop and outer loop, similar to the click check, right?
Okay.
Just click I check I need to verify every pair of the vertex has a connection, but for the leg I only check there's only one connection. If they have more than one connection, I say, oh, this vertex I had to remove from the graph. So that's why similar way as the check for the click, but just one vertex check, more than one vertex check, and all vertex check for the adjacency list. But there are no adjacency lists. That's why I cannot to use a lens to check this adjacency list for particular vertex has more than 1 degree. If specifics identify the problem as the graph has the edge represented by the adjacency list, right? Then I can use the lens to know how many degree of the one vertex. But I don't know this assumption. That's why I use a similar way for the click check to say this n square. That's why I didn't mention. I didn't mention the loop because I have some problem in the previous homework. I lost the points because TSA I present this loop to verify the the running time. So that's why I lost the points.
Okay. Okay.
So this is contradictory.
You have to stop. You have to stop. You have to stop. I understand the your problem statement, so I'm going to address it. Because I don't want. I feel like we're going to keep going. So the reason why it doesn't work like that is because if I wanted to verify if all vertices are connected to all other vertices in a given click, right? So if I wanted to say if this vertex is connected to all the other vertexes, say we have here. So this is this one place right here is O of n, okay? And so then when I'm over here and I want to know if this is also connected to all the other vertices, this is also O of n, right? And then same here, I want to verify if it's connected to all the other vertices, this is O of n. And so what I'm doing is I'm doing this O of n times, okay? So this is O of n squared, and that's why it takes O of n squared to verify click. If I wanted to find all the legs, given this massive blob and I don't know what's in it, and then I just want to find this leg to remove it, 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 so forth. Okay. At each vertex, all I need to know is how many degrees this is. All I need to know is how many vertices this is connected to. It takes O of 1 to determine if a vertex is connected to 1 or more than 1. Okay. So if I'm inside one of these vertices, I see this one's connected to one vertex. That takes 1. I see this vertex is connected to a second vertex. That's 2. That's 2 steps, and I know this is greater than 1. So that's O of 1. Okay. If I'm over here and I say, okay, this vertex is connected to something in here, it's only connected to one vertex. I don't have any more vertices to check, so that's also O of 1. And so if I'm doing this O of 1 on all the vertices, and I do this n times, then this is O of 1 times n. And so the overall runtime becomes O of n. And that's why.
But I see the
you don't have
the
to you don't have to
case.
care about you don't have to care about adjacencies list, adjacency matrix, right? This is if I draw a graph and this is how I want to determine the connectivity of the graph. There's a difference between checking to see if a vertex is connected to every other vertex or checking if a vertex is connected to just one vertex. That runtime of that each step is between O of n is the difference between O of n times O of n and O of n times O of 1.
But I check the leg, right? The leg has only one adjacency vertex for particular vertex. But
that would be an O of 1 check.
But I don't lucky, I'm not lucky. I can check out because maybe the first one connected, right? This one leg, but the second not connected. But that's maybe the third connected. But who knows? Just
you don't need to know what you don't need to know what it's connected to. You only care whether it's connected to one or more.
Yes, one or more. Because if I iterate all the adjacency vertex for right, there's only one connected. So this should be removed. So that's why I still need to check all the adjacency list for the n. Right. So that's why n times n squared. Right. I still need to check all the adjacency vertex to verify if there's only one connection. But I don't know, because if I have the adjacent list, it's very simple. Because adjacent list give me one vertex, this is degree 1. I think this is a leg I had to remove. But the question is, the problem is I don't have this kind of adjacent list. I had to iterate all the outer loop as all the vertices.
You have to let me get a word in. You have to let me get a word in. I'm trying to illustrate to you, and I feel like you're just arguing with me, which I understand your frustration, but I'm here to try to provide like the understanding.
I see.
You need to let me get a word in. So I understand that you're saying that in the check, if you were to write pseudocode, you would have 2 for loops, and it would be a nested for loop, and therefore you think it's open squared. But the actual correct pseudocode for that, if you were to check to see how many of these vertices is connected to more than one thing, it's actually a for loop followed by an if else statement. If you check it and there's two edges to it, it has 1 or more. So that's a O1 check. And the second one is else. If it's only connected to one edge, then it has 1 degree and you can remove that vertex. It's not a nested for loop. It's a for loop with an if else statement inside and therefore the if else inside is all 1, and the for loop outside is all n, giving you a total runtime of all n. Again, I don't see a solution, so it might be like you explicitly did it differently, but the naive simple solution is all of n. Okay.
I think the similar we check as the at the click, because I loop all the vertex.
I have presented to you what the runtime would be to check it. At this point, I think you're looking for a regrade feedback, and I think that's a great place to do it in the actual regrade feedback thread. At this point, I can't change your grade. That's not my position this semester. Okay. Like if you do a worse than naive solution, then you have to make sure that it's properly explained in your solution.
I have one problem regarding the thing you just wrote on top of this slide. You said checking for one vertex to check it is connected to all the other vertex in the PK takes OM. That means to check the existence of one edge, it takes O1 time, right?
Yes.
How are you? How can you check it in O1 time? What is the how is the edge represented? Is that represented as an adjacency list?
I mean, it's an adjacency list, but anytime you want to go from an adjacency list to an adjacency matrix, it's all of n squared to make that adjacency matrix, right? And then once you draw it all up, you can just check to see if that adjacency matrix for your click candidate is all ones, and if it is, then you've done it in O of n squared. Like that's sort of like that's like the explicit like steps on how you could do it, but it's also just really intuitive to say checking to see if a candidate click is in fact a click is all of n squared by checking to see if all vertices are connected to each other. Like you don't have to give like the very explicit details of that. Like it's checking to see if all these set of vertices are connected to each other, all of n squared, done.
So is it also correct if I say it's O n cube?
If you say O of n cube, you should give details on why your solution is slower than the accepted solution.
Okay, thank you.
Yeah, it'd be like me saying that DFS runs in O of n plus n. That's an accepted fact. If I say that because I am trying to be clever and I want to be extra slow in my DFS, and I say my DFS takes O of n plus n squared, I have to now explain to you why my DFS is not the standard DFS and why it's so slow. I can't just arbitrarily decide on the slower runtime and let it be an accepted fact. So checking to see if a click is a click, checking if an independent set is an independent set is all of n squared. It's an understood runtime. If you're doing something slower, if you're doing something special, those steps need to be more explicit. All right, I'm going to try to erase this and go with output. So the output removes added vertices from transformation, which may not be present in the Spider-Verse solution. So I already went over this, but a lot of students will just remove their added vertices thinking, oh, all the spider legs has to be vertices that I added. And it doesn't even have to be all or nothing, right? Like if I had a click here, that's this thing, and it came with one leg, and this is actually pretty reasonable, right? Like I may not have all the legs that that are part of the spider, right? And then you add this leg, and you add this leg, and you add this leg, and you add this leg, right? The Spider-Verse algorithm might pick this click, pick this leg, this leg, this leg, and one of the legs that was already on the graph. Now, when you go and remove your added vertices, you've removed this one and this one and this one and this one, right? And now you have this click with this extra leg, and that is not a proper solution, and so that's a mistake. Okay. All right. Transformation depends on the induced subgraph, but does not create one. So if you go and you try to do something with like the transformation, and you just assume that the graph given to you is exactly a spider, it's going to be a mistake, because the output to Spider-Verse is not a set of vertices and edges. It is a set of vertices whose induced subgraph is a spider. So if you're going to start removing edges or doing something weird, you have to induce the subgraph first before figuring out what to do with it. And that's actually one thing. So like if I'm removing legs and I'm saying I want to remove all legs that's 1 degree, I have to induce the subgraph first and then remove all legs that's 1 degree. Otherwise, those legs might be connected to other vertices that makes it so that it's not actually a 1 degree vertex.
Okay. Would you mind elaborate on that induced graph and how do we induce a graph?
You just say it. Like it's not like any special thing. You just say induce the subgraph of the vertices. So what that means is that let's see. Okay. Suppose I have these 3 vertices, and then this vertex is not one I care about, and this vertex is not one I care about. So if I am given 3 vertices, this one, and this one, right? And I go, okay, how many degrees is this vertex right here? It depends on what you're asking. If I ask you how many degrees this vertex is in the original graph, right? This is 1, 2, 3, 4. This is 4. In the induced subgraph, which is this has a degree 2, right? So it's different depending on whether you've induced a subgraph and then saying, given the induced subgraph, find all vertices that are 2 degrees, which would be this one, and this one. Or if you say, without saying induced subgraph, find all vertices that's 2 degrees, it's this one and this one. That's why in the inducing of the subgraph matters.
Is it correct that when we say we induce a graph, we are looking for the vertices and all the edges associated with that vertex?
You're looking for all the vertices that's given in the set and all edges between those vertices. That is what an induced subgraph is.
Okay, all the vertices given in a graph and the edges associated with. Yes. Okay, thank you.
Okay, moving on. Runtime analysis. Again, the polynomial time. This one's less common simply because I think there was smaller information to work with. So try to avoid these going forward. Oh yeah, and does not return no Spider-Verse algorithm returns that. This is super annoying, super awkward, but you always need to handle all possible solutions to your in your output transformation. One of those possible returns is a no, and so you have to handle the no as well explicitly. Okay, these are homework 8 common mistakes as of now, as of when I took this. 1, don't try to say that this is exactly what the end result's going to be. This is just so I can point out any common mistakes. 2, the graders are still in doing their calibration. So some of these might change. There might be different warnings. Some might be added. Some might be removed. Don't sue me over it. But I figured pointing out the common mistakes would be good. Again, students are binding to GORK without. Establishing runtimes on GORK without establishing it, without binding it. Okay. And if you're going to sue someone, sue Jamie, not me. Does not check the subset of facility size. You always have to check the size if it's given as a requirement. Runtime analysis, incorrect phase. Oh, this is high. I actually don't know why this happened.
Joves, I think part of it is incorrect runtimes this time instead of just missing.
Oh, okay, yeah. So
that this is also should be n times m if we're going with vertex cover.
I actually don't know. I think I have like a general solution in my head on how this should be solved, but I've never seen. I hadn't seen this problem before, so I don't actually have like a properly written up solution. I should at some point. So input. Again, runtime is, wow. Okay, there must have been something tricky about the runtime analysis on this one. This actually went up after the previous homework, which is a surprise to me. Construction of L lacks details, which does not accurately represent the original input. So this is an issue that tends to come up when we are crossing domains. So you are going from either, most people are doing vertex cover, which is a graph, going into the Computopia, which is set up to be like a set, right? So you have to be more careful about the inputs when you're transforming from one domain to the other. And so this tends to be a little bit higher on these type of problems. So this is that if you are setting up your problem in such a way that you're saying, for V, add all its neighbors into some set. So if this is like U, X, Y, Z, and you're adding all those neighbors, and then you're saying for U, add all its neighbors. So this is V, and let's say X, Y, Z, right? So the set of V, even though this edge right here is shared between V and U, in the set itself, they're not related. And so that is a mistake. What you want to do is get some representation of this edge into both V and U so that you know that they're shared. So that's a mistake. Sorry, the rate, I keep writing where I'm about to present. On the output, runtime analysis does not return null. That's pretty consistent, 5%. And those are the homework. Okay. So here are the list of problems that I plan to do live demonstrations of. I might skip a few. We are running, we'll see. But I'm going to take a 3 to 5 minute break. You guys can take a 5-minute break. We will come back at 3:25. Be right back. Who has been the meanest TA this semester? And why is it Jamie? Has it been Jamie? Oh. So one of the things I don't think students know about our class is that we have a lot of TAs. It takes a lot of TAs to run this class, and some of the TAs, a lot of the TAs have different roles. So not all the TAs are expected to be on Slack or in the discussions. They have like other tasks that they handle. So just because you don't see a TA regularly or for whatever reason doesn't mean that they're not contributing to the success of this class. Some TAs just really like to interact with students more than the behind the scenes stuff. So those students tend to, those TAs tend to be who you see and talk to. All right, let's start. Here are the problems that we're going to go through. Let's see. Stingy sat is a good one. Special cases NP complete. I don't remember what that is, but I'll do that. 8.10 is like a series of like 5 or 6 problems. I might like cover like a couple of them. The format is a little bit different than what you are expected to do on the exam. So we'll try to get that done well. Click in the IS was asked for, but this was your, this should have been your quiz. Hopefully, we should have gotten like basically a model solution from the quiz. Maybe I'll answer specifics if anyone's confused. Maximum common subgraph. Experimental dish. Hate the wording of this problem. Again, yep, these are pretty good. Okay. So let's go to the whiteboard. Stingy sat. Can you guys see my whiteboard? Sometimes I forget to share it.
Yes.
Great. So Stingy sat is the following problem. Given a set of clauses, each a disjunction of literals. That's just a fancy way to see what see enough. Okay, why is my thing not loading? There. Okay. And an integer k, so that's key detail right there. Find a satisfying assignment in which at most k variables, k again, are true. If such an assignment exists, prove that Stingy sat is NP complete. Okay. So let's copy and paste things. All right. So this is my NP proof. So if you are given the input, so you don't actually have to write this part. This is just my writing style, because when I took the class, one of the things that was in I think in the lectures, and we never really got good sense of, was like you have to establish that this is a decision or a decision problem, search problem, whatever. So this is kind of like how I established that this is a search problem. Don't bother with it. So given the input I, k to stingy stat, and the solution s, we can verify that for all clauses in I, which is the input, each clause can be satisfied with assignments in S. We check n variables over m clauses, so this takes all of n times m. We can check that S contains less than equal to k true variables in all of n time. Overall, it takes all of m to verify, which is polynomial. So notice the key parts of this is that I am going to verify my clauses that are satisfied by the assignment. I established a runtime for doing that. And then I say we can check that S contains less than equal to k, because we have to establish, we have to verify the k sizing. And then I establish the runtime for that, all of n. Generally for these things, like when you're verifying a number, you can just say this is the runtime for it. And again, I could have said it takes all of k, where k is less than equal to n. But instead of saying all that, I can just say all of n time and it's established. It's k is established to be bounded by n with that statement. And then overall, I like to give a summary of the runtime. You have to do this as well. You can't just throw a bunch of runtimes in there and then not say this is my overall runtime. Just like any of the other topics, you have to give an overall runtime. And then I like to remind myself that this is polynomial. This is just my writing style. You don't have to follow that. So that is my NP proof. Does anybody have questions on how I prove that stingy stat is in the class NP? Good, cool. Okay. Oops. All right, so these are my input and output transformations. The idea that is given a set input I, we set k to the number of variables in I. So I have established what my k is going to be, and then we pass in the original I with k to stingy set. This takes all of n times m to count the variables, which is polynomial. So again, a runtime, and that's it. And so notice how I don't say why I set k to this, why I do any of this. I'm just telling you. And this mirrors. Why am I so dark? This mirrors my approach to writing solutions in general in this class. I like to give my algorithm or my transformation as concise and what I need, and then I save all my explanations in the correctness. That's just how I do it. If you want to interweave your correctness in there and then make a final statement, that's kind of okay too. But I find that it distracts me from the focus of each section when I do that. Then the output, I always just do this part right here as the very first thing, return no if I get a no. That way I don't forget. I don't try to remember to do it in the middle at the end. I just do it right up front. That way I get that out of the way, and now I'm focusing on the stuff. And then we return the solution of stingy set as a solution to a set. Now notice how there is no transformation in this line, but I still have to explicitly say it. That say we return this, and that's what we get. And this takes all one time because I'm returning something as is. So notice the two big things here. This is a good example of one. I don't need to do a transformation, but I explicitly state what I return. And two, the runtime of a non-transformation is all one, but I still put that into as a runtime. Okay. All right. Any questions about the input and output transformation for stingy set?
Quick question. You said the of one, or you put of, and I'm quite confused. I'm sorry.
Sorry, what?
For the runtime for the input transformation, you have O of N of O N M, and you said which one should it be?
Yeah, I had the same question about the OMM because you just add a new variable k to the stingy set. No any transformation of the input variable. Why you OMM? Suppose also O1.
I think this is what we discussed before. It takes OMM to count the total number of variables in the class. But if you are given the input, then you can say it's just O1 time.
It kind of depends. I mean, Jamie, is N and M on the given as a CNF given to you?
Yeah, Joves, it is, and I think for like this input here, I think we would accept both O of N, assuming that you just have the variables and you'll count it up and you'll pass that along. We'd accept O of 1 if you assume N is given, and we'd accept O of NM if we assume they're going to count it back, reverse from the literals in the clauses to produce the variable count. So there's a lot of flexibility on this one, and I think if it's clear in your input what you're doing, a lot of runtimes will work there.
Yep. And so what Jamie said is good to know. So when I did this problem as a student, it was very unclear whether N and M is given to us. Now you can assume it is and take your chances. In this case, you don't have to take chances because the TA has explicitly said that you are given to it, and that's fine. But because it doesn't really matter how slow my runtime is, right? I didn't care. I didn't care to ask, hey, do I get N and M? I just say I am going to count it, and that's going to be how slow it takes me to count it. That way I don't have any, I don't have to think about it. I don't have to ask. So it's all N M to count the variables. And that's what I have. You can just say it's O1 to assign K. That's fine too. Any other questions? All right, cool. So then I'm going to get my correctness. Okay, so I was looking at which direction I argued the correctness, and I think I chose number 2, even though I said I prefer 1. I think this was before I had any strong preferences. All right, so the correctness here is by assigning k to the number of variables in the set input, we drop the constraint of less than equal k true constraints in staging set. If all variables in the set input needed to be set to true, then staging set would be able to do so since k equals n, and at most n variables need to be set to true. So that gives me if A has a solution, B has a solution. If the set algorithm cannot find a solution, then because the stingy set input is unchanged, the stingy set algorithm would also not have a solution. This proves that stingy set is NP complete. So this is the if A has a solution, then B has a solution. If A has no solution, then B has no solution. Did I just get disconnected, or is everything okay?
It's back now. Would you mind click away your mouse, please?
Click. Oh, thank you. Okay. Sorry about that. I don't know what happened.
If we were given, sorry, a slightly different question, saying that instead of at most saying at least, would it still remain the same?
If at least
k variables are true instead of at most.
Such that at least k variables assigned to true. Probably just set k to 0. I think that would work, right? It would change the answer. Yeah, certainly. But I think you just if you said at least, I said 0, then at least 0 variables is set to true. So if I have 1, then that's fine. If I have 2, that's fine. If 0, that's fine.
Yeah. Okay, good.
Okay.
When at least k variable, that would make it trivial, because we can always set it to 0.
Yeah, but it's just as trivial as this one, right? I mean, how trivial it is depends on how quickly you can see the connection. I think this is probably one of the easier NP complete proofs. This could have been written as a generalization because you can basically make the two problems equivalent. So this is a good example of like what a generalization type problem would be. But I still wrote out every single step because that's what we want you to do on the exam.
One other thing is that instead of using SAT, you can also use 3-SAT, but I think we were advised not to use.
You can use 3-SAT, that's fine, yeah.
But then in the output transformation, we have to make sure that it has. No, well, output transformation doesn't matter because we just have assigned.
Doesn't matter. Yeah.
Okay.
Yeah, and so this is that's a good question, and this is a good example. So when I say that your problem A has to be able, your transformation has to handle all the possible inputs to problem A, it does not mean that it would end up providing all the possible inputs to problem B. If you started off with a 3-SAT reduction, and your stingy SAT can take on clauses with more than 3 literals, your transformation is never going to give stingy SAT a clause with more than 3 literals, right? Like it doesn't matter. You just have to handle problem A using a black box for problem B. You don't have to prove that problem B will solve every single possible input or even know how that would be solved. That is not what the point of this is.
Hi,
Okay.
Joves. I have one more question because I think right, if the stingy have solutions, stingy set have solution, set must be have solution, right? But negate if the stingy has no solution, we say the set has no solution. I'm not sure this established. For example, if I had 10 variable, right? For the stingy set, I say that the k is a constraint as the 3. But if I say that this three number of variables as a constraint, there are no solutions. How can I say the set no constraint have no solution?
You are not working on a general stingy set problem. You are working on this specific stingy set problem that the k is set to the number of variables.
But NP complete and not set without a constraint is a general problem as NP complete, right? So this is no any constraint. I have the 5, for example, maybe I have 5 variables satisfy the whole solutions, but the 3 is not. How can I reduce from the no solution from the stingy set to the no solution for the general case set?
You don't. That would be the reduction in the wrong direction. You don't care. You shouldn't care. You're trying to say that if I have a input to problem A, I can solve it using problem B. That is what you are trying to establish in your reduction and proof. You don't care that there are certain problems of B that can't be solved because that's not how this reduction is set up. You want to say, given any input to problem A, I can manipulate my input in such a way that problem B can solve it for me. And that's it.
But I say B. So if the B no solution, right? But the B no solution, A no solution, equivalent to the A solution, A have solution, B have solutions. But you are right, A have solution, B must have solutions. But I cannot say B no solution, A must have no solution. So this suppose
that's what
equivalent.
This statement is. That's what this statement is. If A has no solution, then B has no solution.
Yeah, this is one way. But I say if B has no solution, A has no solutions. This also say that A has solution, B has B has solution,
well,
right?
that's why you have to argue both of these directions in order for them to equate to that it's an if or only if. So if A has a solution and B has a solution, and if
but B had no solution and no solutions. But I have some counter example, right? So B no solution, A not no solution.
So before you go through your counter examples, I do want to point out that this correctness argument of if A has a solution, B has B has a solution. If A has no solution, B has no solution is established fact in this proof. This is not something I came up with, nor is it something that the class came up with. Like this has a long history of being like an established way to prove the logic of it. And I think I want to say that we have a good post about this, the contrapositives crash course by Asia. If you don't quite understand it, oh my gosh, this post is long. You should go read Asia's post. I think Asia does an excellent job of explaining why this works. Okay. All right. I'm going to move on to the next problem, which I need to look up, which is special cases of NP complete, which is 8 point. Sorry, 8.6. What is this? .6. On page 266, we saw that 3-set remains NP complete when the restrictor formulas in which each literal appears at most twice. Okay. Show that if each literal appears at most once, the problem is solvable in polynomial type. Okay. So this isn't formulated in the way that you would we would expect you to do this on the exam, but it is a good exercise to sort of understand. So the idea is that why do we do NP complete proofs? Why do we take a problem and alter it slightly and then reestablish that the slightly altered problem is NP complete? Why do we bother doing that? One of which is because it's good to understand what changes a NP complete problem to a P problem, what changes a P problem to NP complete problem. Finding those boundaries kind of help you establish, can you even find a fast solution for the problem you presented? You know, or maybe you can't. Maybe you just kind of go, you go, okay, well, this is an NP complete problem. I should just start with approximation strategies. The other thing is like, this is kind of how super smart people are trying to solve the P equals NP problem. You keep sort of like finding alterations of the problem such that, you know, you find that barrier of like, okay, flipping this one thing changes this to P, flipping this one thing changes to NP. If we're ever going to find that there's space between the P problem and the NP problem, that's how we're going to find it. We're going to change problems ever so slightly to see if we can show that there is a space between P and NP. Because the idea is that if there is a space between P and NP, then P does not equals NP, right? Because if there's some problems that are in that middle space, then surely those two classes of problems are separate. If there's nothing in between those two spaces, if we can never ever find one, and that's a problem. It's really hard to prove the non-existence of something. But if we never ever find one, then it might result that P does equal NP because there's nothing in between them. So finding that what's called NP intermediate, not a topic for this class, but if you ever are interested, finding a NP intermediate problem proves P does not equal NP, and that's why people do this. So the question is, if we change this one thing, can we make the problem into a polynomial problem? And the answer is yes, because the question implies it, and the algorithm to do so is here. So I am going to use the product type matching that we learned in 7.3, which you did not, but that's kind of how this problem can be approached. So we know that each literal can only appear once. We can set up a product type matching problem such that one side is the variables, the other side is the clauses of the special set. We set an edge for each variable to each clause it appears in and set the capacity to 1. This is at most 2 edges. Most 2 edges. We then attach a source to all variables and a sink to all clauses. These edges also have a capacity of 1. Finally, you run Edmonds carp and check that the max flow size is equal to the number of clauses. And so since the correctness on this is since each variable has an incoming flow of 1 from the source, each variable can only be used to satisfy 1 clause, which is okay since we know that each literal can only appear once. So if x can only be one of x or not x, then it can only satisfy one of the 2 clauses it might appear in, either as x or as not x. And since the x node will have 2 exit flows set to 1 capacity and the incoming flow is 1 capacity, then only one of the exit flows can be satisfied. Finally, we check that f equals n, which tells us, oh, m clauses are satisfied. If it is satisfied, then look at each variable. Okay, so you can keep reading this, but I do want to sort of give an illustration of what this all means, because I'm sure that's all sounds well and good, but let's see. All right, so suppose we have this clause here. Let's say u or, oops, let's not do that. X or y. Okay, and so here is a valid expression, right? We have one literal showing up only once on each of this, x or y, and not x or not y. You can't set x and y to true because then this becomes false, so you have to set one or the other. And we now want to know what is our polynomial time solution to solve this. And obviously, like, this is a 2-step problem. You don't have to think too much about it, but I just wanted to show how this can be expanded, and this is the easy one. So if on the left side here, we say that this is x and this is y, okay. And then on this side, we say the clause is x or y, and this side is not x or, oops, not y. And then we make this up by part type graph because x and y are not connected, and the 2 clauses are not connected. This goes here with a weight of 1. 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 And then I have some, oops, some source, and I put 1 here and 1 here. And then I have some target, and I put 1 here and 1 here. Okay. What's going to happen is that x gets a flow of 1. And then from there, it can either satisfy one clause or it can satisfy the other clause. And that's it. It cannot go to both clauses at the same time. Y also gets a flow of 1 coming in from the source, and it can only either go to the top clause or the bottom clause with a with the flow of 1. And we do this for any given variable and any given clause that variable appears in as one of the literals. And you can only have a maximum of 2 because each literal can only appear once. When flow comes out of source, we have a maximum of 2, right? And then if we choose the following path, this one, right, and this one, okay, we have satisfied our max flow problem, and we get a flow of 2. And since I have 2 variables, and I have 2 statements, I have 2 clauses, and I have 2 flow, then in that case, I have satisfied my my thing. Now, the other thing we could also do is S can go this way, right? And then X can go this way. And that's also a valid solution. That would mean that X is set to false and Y is set to true. And that also gives me the right solution. So what does this look like if you cannot get a proper solution? So let's say we do what's another good way to do this? We think. Oops, why? Does this work? So if Y is true, X is true. Hold on, I have to think about this. I need to make it so that I have two of these and I can't actually set it.
You can just create a very simple one, X and not X.
Oh yeah, that's true. That's true. That's good. Good thinking. Oops. Good thinking. All right. Yes, that would good one. Actually, let me try on the bottom. Might be easier. Okay. So all right. So if I have X and not X, right? So then I would expect my X right here to have a single source. This has 1, and then this actually has 1 to the X, and then this has not X. This is also 1, okay, and then this is 1, and this is 1, and that's my T, okay? And so I'm expecting my output flow to match my clauses, because that means every clause is satisfied. If I have 5 clauses and I have five edges coming into T, and each of those are filled, I would have a total flow of 5. So this is impossible to get a flow to. So S comes to X, right? And then I can either satisfy the top one or I can satisfy the bottom one. I can't satisfy both, and so therefore this doesn't have a solution. So this is how you take this problem and you turn it into a bipartite, and then you run max flow, and that's how you get the proper solution. And we know, and you're gonna say, well, isn't Edmund-Karp's pseudo polynomial? That is true. No, sorry, for Fulkerson is pseudo polynomial, but Edmonds-Karp is a polynomial runtime. So this would become a polynomial problem. Okay. And then let me, so that's my correctness. That's basically what this says, and my runtimes. All right, creating the bipartite is O of n, since we know each literal appears at most once. Oops. Then usually we can run either Maxwell algorithm, but we are looking for specifically for polynomial time solution. So we will use Edmonds-Karp, which is O of n m squared, assigning each variable after running Edmonds-Karp takes O of n, and over runtimes O of n m squared. And that is how we turn a NP hard problem, NP complete problem, into a polynomial problem by making a few changes. Okay, any questions? All right, sounds good. 8.9 heading set problem.
Jovis, sorry, I think B might have missed part B for that problem, unless I was not paying attention.
Exactly what I did. I'm sorry. Let me go look at that. It was a test. You passed. All the other students, you weren't paying attention. I'm just kidding. Show that independent set remains NP complete even in the special case when all the modes in the graph have degree at most 4. So the idea here is that if we were to take a similar approach by changing just a slight bit of what the independent set problem is, can we also make that into polynomial? And the question, the way it's asked, implies no, and so we will do a NP complete reduction to show that. Oh, maybe we don't. Maybe I just argue it. Let me see if this makes sense. I think I just argued it because I didn't really want to do the entire like reduction from 4 set to independent set. I mean, you could do this like start from scratch, but the way this problem was worded, I didn't think I had to, so I'm just going to go with that. Okay, so we know that 3 set to independent set is proven. If you haven't, you should go see 8.3. I think that's the section. And then we know that 3 set remains NP complete even if each literal appears twice. Again, check 8.3. And I think that's like the way they wanted you to argue this is that what problem is this? 0.6. Yeah, it goes go on page 266. Go read this and then do this. And so because we know that, then we just need to show that the 3 set with each literal appearing twice maps to a graph with all nodes having degree at most 4. So if we can prove that those two things are equivalent, then the proof that was given to us on page 266 also proves this. So we know that to go from 3 set to independent set, we encode each clause as edges between each literal. So x or y or z gives 2 edges from x, right? You get one x from you get one edge from x to here, and then one edge from x to its non-x counterpart. We also know that x must have an edge for each occurrence of not x. Since each literal can only appear twice, edges from x to not x can only happen twice. So for each node of x, one edge to each literal in the same clause, which is max 2, because we already said that each literal can only prove twice, and then one edge to each not x literal, because that's how they work. They have to connect. Keep an eye on the reduction from 3 set to IS to see why that is. And so the total is 4 degrees max. So that means that because we know that this is true, we are making this right here equivalent to this, and therefore we know that it is considered NP complete. And if we wanted to look at this, each literal appears twice. Two edges from x. So what's the problem statement? I'm trying to remember. Show that independent set requires them to compete even in the special case that all the nodes in the graph have degree at most 4. 3 set, yeah. Why is I think I'm gonna type that wrong. There's 2 edges from x. I think that's supposed to get 1 edge from x. Okay. And so what that ends up kind of looking like if I can draw this directly, is that if I have x, y, z, I end up with a edge to x, an edge to y, and an edge to z. And then because we know that x can only appear in twice, right? Each literal can only appear twice. Let's do that. That right there is one edge. That right there is one edge. And then if I have another graph here that says not x, y, and then here if I have dot x or z, is that how you draw it? Hold on. Let me bring up my book.
Sorry, I think what you previously wrote is correct. The class, the 3 literal class gives 2 edges from x, because when they convert the 3 set to independent set problem, what they do is that for each literal, they, even if it's the same, they create different vertices.
Okay, that makes, yeah, okay, okay. It's hard to go
I
back.
agree that the class should give 2 edges to x. What you have before is correct. And then the graph that I think you are looking for is 8.8. It's on top of page 249 on my PDF versions.
Okay. So let's paste that in. Much better graph. Okay. X. Yep. So this actually just kind of draws it up for us.
Yes, those are the ones that only appear twice.
Yeah. So here we have not y, x, and z. And then x is connected to the not x. And then this x is connected to this not x. And then this one is x, y, and z. And then so each of the x is connected to the not x, right? And so that when you want to do an independent set, you can't have this x connected to this not x and this x connected to x. So this example that they give actually is follows the problem that each of these only applies twice. And so basically what it's saying is that because we know that oh my gosh, why does this he having if the question is asking, show that independent set NP complete within the special case that all nodes in the graph have degrees 4, this end up with each of these having degree 4. This happens to be 3 set. So the question becomes that, like, if this was not 3 set, right? Like if you had an additional variable in this clause, that would expand some of these connections. But because it only has 3 possible clauses, and then so these connections can only equal 2 connections, and this x can only ever connect to 2 non-x's. This can only max out at 4 connections rather than anything more than that. And so by proving that that is equivalent to this graph, now we know that go from 3 set to s, we encode each clause as edges, and then we also know that x must have an edge to each x. Since each literal can only appear twice, edges from x to not x can only happen twice. So that gives us exactly the max 4 that we have decided. And so this proves that this is also NP complete. This is not a formal proof. If I was to write this for the class, it would be like, much more thorough and detailed. But I think because it's telling us to reference some of the earlier proof that this is sufficient. Any questions? Do I have a runtime for this? I don't think I have a runtime for this. I think this is just a exercise in arguing. It's not really like a formal proof. All right. Next one is heading set. So heading set. So the question is, in the heading set problem, we are given a family of sets S1, S2, ... Sn in the budget B, and we wish to find a set H of size less than or equal to B, which intersects every Si. If such H exists, in other words, we want H intercept Si not equal to empty set for all I, showing the heading set is NP complete. So what I like to also do, and you don't have to do this, is like I like to right up front put down what I am trying to do the reduction from, or kind of like a mission statement, I guess. It kind of centers me around to know what I'm working from. I think I have seen some students write their solutions, and at no point is it really clear if they're like reducing from click or IS or some other problem. And if it gets like to the point where by the time I finish the solution, I have no idea what you're reducing from, that's a bad thing. So in order to prove heading set is NP complete, I would reduce vertex cover to heading set in polynomial time. We know that vertex cover is HP complete. Okay. Okay. You remember how I told you guys that to prove a set intercept, it's consider O of n squared. Yeah, O of mn squared, and I said that given enough like explanation, you could do it faster. And so don't be clever. But when I was writing this as a student, I thought that was so awesome, so I decided to be clever. And so my my runtime is actually a little bit faster. I would not encourage writing it this way too much. But it is kind of like if you wanted to look at it. So given an input, we look for a solution if it exists, return no if not. N is the number of sets in S. N is the number of unique elements in S. Now, I absolutely hate the way that this problem was worded because it makes the N and M super difficult to work with. It's not because I want N to be the number of sets in S or that I want M to be the number of total unique elements in S. It's because this right here already set it as N. And so I just kind of work with that. Otherwise, I would have flipped these, but try to work past that. So given this, family of sets S1 to Sn and a budget B as input, we set H to we and a set H to verify. We first check that the size of H is less than or equal to B, right? So always check the size of the things you are trying to verify. So that's one key step. This takes O of M because H cannot be more than the number of unique elements, right? So my heading set of H can't be bigger than M because if it was, it would have elements that wasn't in my set of sets, and that makes no sense. So that is how I establish O of M because of that. Okay. Next, we check that H intercept Si equal to the empty set. This is the problem statement for OI. So you need to verify the second piece. We can do this very similar to set. So that for all sets that's an element of this family of set, we establish that some E in that set is also in a heading set by making H a Boolean array. So if you were to do this using just a set of variables, and you wanted to say, you know, for this set, do a for loop of everything in this set and check it against every single set in the hitting set. This would be normally, and you know, you could easily just declare this to be O(m)n squared, and that'd be fine. But because I turned it into a Boolean array, very similar to how a set works, and I'm just checking directly into it, it is an O(1) check on each variable to see if it's in my hitting set. And so I have reduced that to O(m)n, which is the same as how a set verification is done. And that's all I did. That was extra. Okay. Any questions on the NP proof?
I think you should switch m and n. It's m squared n, not mn squared.
Yes, that is the type of mistake you make when the problem statement is a pain in the butt. Thank you. Yep.
So if we are reducing it, you are reducing it from vertex. Okay. Never mind.
Right.
Thank you.
Hi, Emily. See Emily happily in chat. It's great. So fun story. This is a side effect. This solution actually failed a couple of students. And it's actually what ended up being the downfall of me sharing my notes. I used to share this solution, and students aren't supposed to make use of the solution. They're just supposed to use it for reference. One day, I saw a very clever way of verifying hitting set, and I was like, oh, that's really smart. And then when I looked into it, I was like, this looks really familiar. And then I realized it was copied word for word from my solution. And that's considered plagiarism. And so that student ended up getting written up and unfortunately failing the class. So if you ever use any of these solutions that you see in office hours, whether by myself or another TA, one, don't write it word for word. That's against the rules. You're supposed to write the solution on your own. So even if you copy something from office hours, that's not allowed. And two, you should cite it. Like this is a way to sort of protect yourself to say, oh, I saw this in a previous semester. This is what gave me insight on the solution. But write the solution on your own. Copying anything word from word is not okay. All right, moving on to the input output. The hitting set. All right. So given our graph GVE for and B for the vertex cover problem for each edge in E, and this is the whole idea of like when you're doing transformations, you have to make sure that it's okay to assume that the graph into the problem that you are using is in the structure that you want it to be. That's fine, but you have to go through and tell me what are you taking that graph and how you're turning it into the hitting set. Okay, so for each edge UV and E, add to S a subset that represents that edge. Okay, S and B are the inputs to hitting set. So remember, you have to pass in B, even though this B is provided. It's the exact same B, but you can't just like assume it carries over. You have to explicitly establish that B is also passed in. It takes O(n plus m) time to create S, and it is polynomial. And notice how I don't explain why I did this. It's actually a very short and concise transformation. I never go into the details of like why I'm doing this. You can if you want to again, but this is just how it. Again, the returning no when the algorithm returns no. Return H as a solution to vertex cover. So H is going to return elements, right? And those elements are vertices. So I can just return H as the solution to vertex cover. It's going to give me a solution as, like a set of vertices, and that set of vertices is exactly what my vertex cover solution is. And then it takes O1 to return in this polynomial. So pretty simple. And then I'll explain the correctness. In a second.
Sorry, in the output transformation, since we're going from a set back to a graph.
We're not going to a graph. We're going to a set of vertices.
Going to a set of vertices, but the vertices are part of a graph, right? So if we create a graph with those output solution from a heading set, would that still be valid?
Yeah, so like if I told you that my vertices, or right, that's a set of vertices, and I told you my heading set is a set of elements. Is there any difference between these two things in terms of representation?
There's a representation now, but since it's a different, I don't know. Initially, you said that if we're going from graph to another type of problem, then we have to convert it back, something like that.
Yeah, but like if you have set up your transformation such that you're using those vertices exactly as elements in your heading set, and then when you return those elements as a heading set, those represent vertices as a one-to-one exact like representation. There's not much more you can do about it. Like there's no there's no sense of saying my A in the heading set is an A in the vertex as a vertex. Like if you're transferring from like like if I was to transfer it, not that this is the solution, but if I was to go from a set UV and I wanted to get it back to an edge UV, that takes transformation because they're two different, they're represented differently. One is a set and one is an edge. And so that I actually have to say, okay, well, transfer each set into an edge. But if I'm just doing a element vertices, those elements are just represented vertices. And notice how right here I say a subset for each edge UV, I do say that I turn it into a subset because it's a different representation.
Okay. Yeah.
Right. And then the correctness. This is one of those situations that I found it was actually easier to describe the equivalency of the two problems. And you can do this separately. That's perfectly fine. But the way I argued it is that since every edge creates a subset in S, the heading set algorithm serves the vertex cover problem of finding a set H of size B such that all sets edges is in S are hit or covered. Like those words are in this problem setup is equivalent. So if a subset, aka edge, in S shares an element, aka vertex, with H, then it is hit or aka covered. The two problems are considered equivalent. So if the two problems are equivalent, then if vertex cover has a solution, then there's a heading set equivalent solution. If vertex cover does not have a solution, heading set should also lack a solution. So if A has a solution, then B has a solution. If A has no solution, then B has no solution. So this is the second type of argument. Okay. Any questions on the heading set?
The hidden set, the only difference between the hidden sets and set covers is the hidden set is looking for a set that intersect all the sets. So intersect all the sets, and then the cover set is when you do a union, all the unit member are covered.
Correct.
Thank you.
Yes. Okay. Next problem is NP complete generalizations. Right. So this is the set of problems. I am going to go over a couple of these, but not all, because I don't think they're I think it's just more important to sort of see like how some of these work. Now, first of all, I'm going to say do not do what I'm about to do on the exam. If you screenshot this, show my solution, and say, hey, Joves does it this way, why did I lose points on the exam? You will lose points on the exam. I'm about to go through some generalization because the question asked specifically for generation technique. And that is a much more simplified way of solving these. That is not what you should do on the exam, okay? We agree on that? Let's see, which ones are good? 8A is the one that you were giving a solution to, right?
Yes.
Right. So you guys don't need a solution to that one. I don't think. Let's take a vote. If you were to get 3 of these, which 3 would you like to see?
Set cover.
Set
And math
cover.
set. And A. All the graph one.
All the graph ones. So A, C, and F. Someone wants G. I'm not gonna G, C, and B. I have a solution to G, but I don't think that would be too helpful. It's a very long-winded solution. You guys are gonna listen to Jamie? Are you serious? You're gonna let Jamie con you into seeing a solution for G? Don't listen to it. Someone took a vote away. All right, let's do A first. Let's do A real fast. I do think A is a good one to understand. Okay. Oh, I think A is a good one to understand because when I do 8.15, you have to understand why it's very different from A and it's a different problem. So let's go with quick to isomorphism.
I have a quick question. Yep. Are B and G reducible from something we've seen in the class? The longest path and the...
B uses Rorata path, which I think is covered in the book, but not in the lectures. So you can more or less safely ignore that. Okay. G is a Rorata cycle to reliable network, and I would say that you can safely ignore that too.
Okay, great, thank you.
So yeah, don't listen to Jamie. That guy. All right. So from click to subgraph isomorphism, subgraph isomorphism is the given an input to undirected graph G and H, determine whether G is a subgraph of H. That is, whether by deleting certain vertices and edges of H, we obtain a graph that is up to renaming vertices identical to G, and if so, return the corresponding mapping of G and H. So remember, in this click to subgraph isomorphism, the solution is the mapping, which is key. You need the mapping to be able to do the NP proof. So you verify by checking that for every V that's in in a graph and every edge that's in our edge set of between G and H, that they map to each other, that they are that there is some mapping for every vertex and every edge between G and H. This is just all of n plus m, assuming H is in HC matrix form, or all of n squared if you have to build it. Yeah, because you don't know where all the mapping that gets returned is likely to be in some sort of matrix form, so that you can verify that the edges exist on from your subgraph to your original graph. Yeah. Because if you think about it, it has to be OM squared, because not only do you have to verify that that every edge that is in one graph is in the other, you might get an edge that's in the subgraph that's not in the original graph. And so if you give me a subgraph that's like a bunch of different edges that's not in the original graph, it's going to be OM squared for me to check the entire original graph to see that, to find out that those edges don't exist, right? So it ends up being OM squared. And then so our input transformation is that given hk, create a complete graph G with k vertices, which takes OM squared. Given S from subgraph isomorphism, return the map vertices as a clique of size k, which is ON. And setting G to a complete graph of size k means that a subgraph isomorphism will find it as a subgraph of H if and only if H contains a clique of size k. So what we want to do is that if we have some arbitrary graph of, say,
A quick question: what does N and M stand for here? Are they the number of vertices in G or in H, or maximum?
Whichever is bigger. I'm guessing G, because H is a subgraph, right?
G is a subgraph.
G is then it's H. I guess technically technically N and M is the total number of vertices and the total number of edges between G and H. Yeah. Okay. So so hold on. With this. So H is the first graph, right? Right. G is okay. So if I have some big graph H that I don't know anything about, and I want to know if it has a clique of size 5, right? What I would do is I would create a clique of size 5. Okay. And I would say, hey, subgraph isomorphism, can you find this subgraph within my H graph? And if it can, then that means that within the H graph, I have a clique of size 5, because that's how the mapping would work. And so that's how I use subgraph isomorphism to find a clique. Okay, does that make sense? Any questions?
I have a question.
Okay.
Okay, so what is missing here to, like, prove this properly as an NP complete proof? Is it in the correctness portion where you just say isomorphism will find it as subgraph if and only if H contains a clique of size k, and then just leave it at that and don't elaborate further?
So I actually elaborated a little more. I explained this, but like if I was to make this like super general, I would say this. I would say the input, output, and I would say that my correctness would be, by establishing by creating a clique for subgraph isomorphism to find a subgraph of in H. I have asked it to find a clique, and that's it. That's all I would have to say. Like, I've argued the equivalency, and that's basically just a general enough statement to make them to say that they are NP complete.
Okay, so aside then from the correctness, is this kind of close to what would be an exam proper answer?
Your exam question is not going to be this general, is the thing I'm trying to tell you, is that like these questions are designed to be pretty much like one step away from getting the NP to getting the equivalency. And so therefore when you go argue it, it's about like one step away on each transformation, and then one sentence or two on the completeness is enough. but we are not going to give you a problem like this. And if you try to solve it using a generalization technique, you're going to have a bad time.
Okay.
Okay. What is the next one? Someone wanted max sat, right? So that is, given the CNF formula and integer G, find a truth assignment that satisfies at least G clauses. So this one's also super simple, which, I mean, these are all meant to be like super simple. Otherwise, you wouldn't be able to really call them generalizations. We verify by checking each clause with the assignments in S is all of N. And then, oh, I didn't verify K. Hold on. Oops. Let me edit that real quick. Wait, why can't I? Max set. Let me reread the problem. In interest case, find the truth assignment says at least G clauses. Verify by checking clauses with the assignment in S. I'm also writing very little on the actual like steps here. Like on the exam, you would expect to be a little bit more detailed. So verify by checking each clause with the assignments in S and that G clauses are satisfied. So that you solve Mn. The input transformation given I, passing I and K equals M, where M is the number of clauses in I, and then the output given S from maxsat, return it as the set solution, all of 1. And the correctness is that by setting K to M, maxsat will return a solution that satisfies all clauses in SAT, and therefore they're equivalent. And so if and only if blah, 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 is all sort of taken care of. I think in terms of like truly, if you wanted to be even more like simple on the generalization, you could just simply like argue equivalency, and you wouldn't even really have to do the NP complete part, because the NP proof part, because the NP proof part handles itself once you have argued that the two problem is equivalent. So the way to verify one is the same way, basically the same way to verify the other, but we're not going to go that skim. Any questions on SAT to maxsat? Okay, good. And then someone wanted set cover. Is that the other one that students wanted?
Yes, if you can just go over the two generalizations of set cover. I think Dr. Brito went over one and then left another one. The book said there's a two.
Which two other?
Yes, I don't know.
Wait, what was? Hold on, let me see what the problem. Set cover two. No, which one did he do?
He slightly mentioned his vertex cover, as when I asked it, it was close to homework 8, so he didn't divulge too much about it.
So vertex cover is the most obvious one. What's the other one? Maybe set? I don't know what the other generalization one would be. But I'm going to give you the vertex cover one because that's the one I have written down. Sorry. All right. So when I read this, I didn't even know what a set cover was. So I pasted the definition in here from Wikipedia while I was at it. Right. So the idea is that a set cover is given a set of elements called the universe and a collection S of M sets whose union equals the universe. The set cover problem is to identify the smallest subcollection of S whose union equals the universe. For example, consider the universe of 1, 2, 3, 4, 5 and the collection of these clearly the union of S is U. However, we can cover all of the elements with the following smaller number of sets. So I put in here, assuming that UV and VU are the same edge, which is trivial to do, verify by checking that my size of S is less than equal to. Wait, why did I? Oh, sorry. This top one is not related to how we verify. This top one is just a note that I'm putting into here for myself that I'm going to use when I convert from vertex cover to set cover, that UV and VU are the same edge. I don't want to have to deal with like dual edges and stuff like that. So we verified the set cover by saying that we check that the size of S is less than or equal to K, and the union of S is equal to the union of I. We can do this in O of n times n because you're just going to go through every set and go through all the number of elements and put them together. The other problem for set cover is 3D matching. I'd have to really think about it. Okay, I just realized that it was Jamie who said it, so he's probably trolling me. Oh my gosh, okay. Anyways, so the transformation is that for each U in V, create a set for each vertex in V, create a set UV for every, okay, so a set for every edge in E. Pass in sets, all edges in K to set cover. All of n plus n. And then on the output, we match each set to the U, to the vertex it was created from. This can be done by checking the first two edges in S and getting the shared vertex. Return list of U, which is all of n. Correctness by creating a set for all the edges for a given vertex. We create sets that represent the edges a given vertex covers. So the set cover algorithm picks at most K sets, which correspond to the K vertices that cover all edges. I think this ends up being exactly basically the solution to homework 8 for you guys. Does this answer make sense? I mean, there's more details that you would have to write for homework 8, obviously, but I think this is generally the same concept. You're basically turning your vertex cover of edges and vertices into the sets and the elements in the set cover, and then you take the set cover, which is the universe, which is the number of subsets that create the universe of your set cover, and then you consider that to be the vertices that cover all your edges in your vertex cover. So it's kind of like the equivalent. All right, any questions on I can totally see why Dr. Brindle didn't go over this, because this is very similar to your solution in homework 8.
In this case, couldn't we also return the output as is in constant time like you did for the heating set?
No.
I don't think so. Set cover returns a set of sets, but vertex cover needs a set of vertex. You need to convert the set to the vertex.
Right. So what you're going to end up getting back on your, where's my pen? On your, so this is, yeah, that's a good question, but it's not quite the same. You know, sure. Oh my gosh, where am I on my? Did my thing not sync? How do I refresh this? Guess I'll leave and come back. Oh, cool bug, love it. Whiteboard has this on Android has this super annoying bug that if you bring up a menu, that menu, whatever like method that calls that menu, becomes attached to the home button. So then when you click the home button, it opens the menu instead of going home. I have no idea how that bug even happens, but that's what it does. It's super irritating. I have to like carefully not click the menu. Okay, so if I was to, so what ends up happening on the set cover side is that you have this like, you have this set that represents a vertex V. And in that vertex V, your set is basically like V, A, B, 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 C. So it's all the edges that are attached to this vertex, right? And when you select this set as one of your set covering sets or one of your vertex cover vertices, you have to extrapolate from that this. So it's not just a one-to-one. You have to map each set so that it is to the vertex. And this can be done by checking the first two edges in S. So you check these first two right here, and you go, which one is the shared vertex? And it shares B, so that then I know that the entire set is represented by it represents vertex B. Does that make sense?
Yeah, thanks.
Okay. Cool. So yeah, what I'm saying is that when you hit this menu button, right, and then you hit this home button, that works as expected. On the Android app, for whatever reason, is this still the right? Oh, that's the wrong point. This one. On the Android app, for whatever reason, it has the exact same layout. But after you click this menu button, this home button now gets mapped to this menu button. And I just actually have no idea how that happens. Like sometimes I see a bug in software. I'm like, oh yeah, I can totally see how that happens. I don't know how the functionality of a button click gets remapped to a method call on another button click just randomly like that. It makes so little sense to me. Yeah. All right. Let's see what the next problem is. That was it, right? That was the 3 that was asked for the generalizations. I don't want to delve too long in it. I don't want to like get people into the mindset that like they should write solutions this way when I really don't want you to. So I don't want to like do too many of them. So this was A, C, and F, and someone asked for A, C, and F, I think. Yep. Okay. Next problem is 8.14. Does the student who asked for the problems, I know you probably just copy and pasted the practice problems that Dr. Brittle suggested. Do students actually need 8.14 explained, or is that something we can just skip?
That's a quiz problem. I think it's covered.
It's the quiz problem, which is why I'm saying, like, do you actually want to see that, or can we skip it? Okay, cool. We're gonna do 8.14 and then take a break. 8.15. 8.15 is actually really interesting, and it took me the longest time to solve because I misread the problem. And then when you misread the problem, it becomes super, super difficult. And then you make assumptions that are just wrong. So let's go with that, and then I'll talk about it. Okay. Maximum common subgraph. You're given two graphs, G1 and G2, and a budget B. And the output is two sets of nodes such that V1 is in the is a subset of V1, and then V2 prime is a subset of V2, whose deletion leaves at least B nodes in each graph and makes the two graphs identical. Now, if you read the isomorphism problem, you might come off thinking that these two graphs, like the two graphs that are remaining, is a mapping of one to the other. And then you get to the point where like, well, how do I verify this with, you know, without a so how do you get the mapping when you go to the verification? Because getting that mapping is actually and we've proven is an NP complete problem. So what this problem is actually asking is that if I take one graph and I take two graphs, and they might have different vertices in both of them, when I remove vertices from one and remove vertices from the second, what I'm left with, and the key word here is two identical graphs. And when it says two identical graphs, it means the same vertices and the same edges. It's no longer a mapping. You end up with two identical graphs where all the vertices and all the edges are exactly the same. And therefore, when you have that, to check one or the other is becomes rather trivial. It no longer is a matter of trying to get a mapping. And so, a solution to this problem . All right. So like again, I like to establish what I'm going to use. I decided to use click. So I will prove that I can reduce from click to OMSCS, which is short for maximum common subgraph. So our NP proof is that given the input, look for a solution, return no if not. So we are given G1 and G2 in a budget B with the solution V1 and V2. We can verify the solution by checking that when we get the difference in vertices, it's greater than equal to B, and then also that when we do this, it's greater.
That's less than or equal to.
Greater than equal to? Should it be less than equal to? Did I miswrite?
It's that leaves at least B. Oh, it's not the difference greater than or equal to. It's the remaining set that greater than equal to.
Yeah. So if I take V1, which is my original vertices, I remove the V1 vertices, I am left with at least V vertices, right? That makes sense.
Yeah,
that makes sense.
Okay. Yeah. So at least B and at least B on both of these, right? So that's part one. That is V1 without V1 prime is the size of at least B, and V2 without V2 prime is the size of at least B. Yeah. So that's the first claim. That's the size constraint that I have to verify. Secondly, let G1 prime equals G1 without the vertices in V1 prime and without edges attached to V1 prime. So remove all the vertices and all of those edges. And then G2 is similarly the same for the V2 prime and G2. And then we verified that G1 prime and G2 prime are identical. That is, G1 prime and G2 prime share the exact same vertices and the exact same edges.
How can that be? They are from different graphs. You mean they are labeled in the same way from 1 to 8?
Yeah. So like if I had like, you know, a I would expect these two to be different graphs, right? But once I remove all this and remove all this, I can check that A and B, the remaining graph A, B is identical. So the same vertices and the same edges, even though they started from different graphs. That's what it means to be identical in this case.
I see.
I think I actually looked this up.
I think this will make the reduction really difficult.
I don't think so. I mean, I'll show you my solution. You can tell me if it was really difficult. But like the other way to look at this is that if you do a mapping instead, the solution to the output to this is not a mapping. There's no mapping. It's just a set of vertices that you're deleting. So if you're assuming this comes with a mapping, it doesn't. And then how do you verify that one graph is isomorphic to the second graph? And if they are isomorphic to the second graph, which assumes that these vertices are the same, to find that isomorphism is NP complete, as we have just proven prior to this problem. So it has to mean the two graphs are identical. There's no other way. Like if you were to have to discover that mapping, we wouldn't be able to figure this out. Not in NP, not in polynomial time for the verification. And this is the part that I didn't understand. I was like trying to do this isomorphism thing, and I was like, I don't think I can. This takes away. Oh no! When I stretch this, it doesn't. Okay, that makes sense. Okay. And that's I was stuck on that for a little bit. Okay. Any questions on the NP proof? Okay. Moving on to input and output. All right. So given the click input G and K, we create G2, so a complete second graph, such that it is the same vertices as G, but fully connected. We pass G1 equals G, and this G2, and we set B equals to K into MCS. G2 takes all of n squared time to create, passing in the other values takes all of 1 over 1 times all of n squared, and is polynomial. Output, return no if the MCS algorithm returns no. Given the solution to MCS, let C equals G1 without vertices V1 prime. So I am given back V1 prime. I need to take it out of my G1, and that is my click. Return C as our click solution. C takes all of n to build and is polynomial, because I'm just taking this original graph and removing a bunch of vertices. And then I will paste the correctness, and we'll talk about it. Okay. By setting G2 to a fully connected graph version of G1, we make it so that no matter what vertices MCS removes from G2, the remaining G2 prime is a click. The only way to remove vertices from G1 such that the leftover graph is identical to G2 prime after vertices are removed would be to find a click of size B within G1, since whatever was removed from G2 would leave behind a click. So if there is a click in G1, then there is a solution to MCS. Now, if click has no solution, then there would not be any vertices that MCS can remove from both G1 and G2 to create a B-size match. Since no matter what's removed from G2, a click remains, so G1 must contain a B-size click. And since G1 is the original graph, it would need a K-size click. Okay, so what does this all mean? Suppose I have a graph into my click that has a size 4 click in it. I'm trying to find it. I don't know where it is. I'm trying to find it. And the rest of the graph has some random vertex. Some random vertex. Okay. Set. I'm trying to find the location of this click. So what I can do is I create a graph. 1, 2, 3. Okay. Such that everything is connected to everything. I know this is ugly, but you kind of get the picture. Okay, so it's all connected, right? And what does that do for us? So suppose I have a click of size 5. If I was to completely remove this vertex, all the edges that came with it, that actually leaves me a click of size 4. When you remove a vertex from a click, whatever remains in that graph is still a click. Draw a picture of like 5, 6, 7, 8, whatever, and then just start removing vertices and see how that works out. It just kind of works out that way. So what I'm saying is that if I wanted to find the size 4 click, and my maximum common subgraph is trying to remove as many vertices as it can from my made up graph, such that we still match my original graph. On this graph, on this graph down here, it's gonna remove whichever vertices. It doesn't really matter. Like it just it'll remove the same vertices that represent this one that we don't need, this one we don't need, and this one we don't need, and it'll keep the last 4 vertices that make a click, and it'll keep the exact same 4 vertices because it's going to keep them identical. So my argument is that in order for it to remove enough vertices such that the 2 graphs match with a budget size B, my second graph, because it's fully connected, has to be a click. Therefore, for it to match whatever is left in the first graph, whatever is left in the first graph is also a click of that same size B. And therefore, I can use that to find my click in my click problem. Does that make sense? Anybody have questions? No? Great. All right, it is 5 o'clock. I think now is a good time for a quick break. Let's come back at 5:06. So go ahead and take a break. Be right back.